And with respect to Apo and Mustafa, I mean, in a very generic way, I mean, both of them have, I think, lots of ideas, but primarily Mustafa is working on basically the digital platforms and seeing how computation somehow can start to play a role. And Apo is more of a kind of prototype guy, really going to be speaking more from a tangible media place and more from a way of thinking about making and thinking and structure and those kind of things. Both of the guys I've had quite a long-standing working relationship. I mean, both of them were ex-students of mine, but Abba worked with me for almost 3.5, 4 years in minima forms and things like that. So there is a sensibility there that is complementary from both sides. And I think in some ways, the conversations that you guys have with them, of course, is going to necessitate that you kind of, obviously show your progress and so forth. But there may be an attention to certain aspects that you may want to focus on. Not so much now, but as we get towards the end of the term and we start to take some advantage of some of the experiments that we'll be doing, I think it's good just to keep in mind a little bit their backgrounds so that you can have more feedback and we can start to kind of shape what we're going to be doing in the studio directly. I mentioned very briefly to some of the students that were here before that I think the goal for the end of this term is for us to be pretty clear about what our architectural problem is in some way, not so much in terms of application, but how we're approaching architecture, how we're approaching matter, and the beginnings of basically how we're going to try to really work on this. So as you guys are developing your skills and we're kind of moving through all kinds of material, I think it's important that we have certain goals in terms of how we see this term, how we see next term. Now, this is not something that is literally like whatever we do at the end of this term somehow is the brief and that's it. Those things are going to evolve, but I want us not to shy away from taking decisions. And those decisions can be about how we're exploring tools, how we start to think about matter, what possibilities are we really exploring when we're starting to look at things more from an elemental way. And I think that this becomes really the foundation of how we're going to conceptualize things. So in that sense, we'll design a brief to make that really accessible by the end of the term so that also the other studios can really comment on what we're doing and, really find a way to kind of shape this stuff together. Okay. So I think the plan for today is to go team by team. I'd like everybody to sit in on everybody's presentations. I think the approach of the Whole Earth catalog, I think, is a good one for us, just so that we can really start to see some specialized research and the kinds of themes that we're talking about emerging. Because in some way, as we spoke about, the elemental is usually not necessarily just one thing in isolation. It's always about the relationship between things. Does that make sense to everyone? Is everybody okay? Okay, yeah. It's good to see everybody's face. It's good to see that you guys are doing well. And yeah, I'd like to start the conversation with you guys and see what you guys have been up to this last week. Okay, who would like to start?
Yeah, yeah. We are the team one. Maybe we can start. Yeah.
If you're a team one and you want to start, sure. I'm totally cool with it. I don't mind. And if you guys want to change it every time that we present, it's totally fine for me too.
Xiaomeng, can you share the screen?
Please give me some minute. I have some connection problem. Sorry, 1 minute.
No, don't worry, it's no stress.
Okay, could you see my screen?
Yes.
Yeah, okay. So let's begin. We are team 1, and sorry. Give me a minute, sorry. We are team 1, the Earth team, and our team members are me, Jiadong, Lekai, and Xirong. And this is our catalog. We do our exploration from the 4 different aspects. The one is background, and then the research based on the Earth and the energy. And the third part is digital simulation methodology. And the next part is problemize the scenario based on the background research and digital simulation methodology. So first is the background, which is separately on and beyond the Earth. So we focus on the planetary urbanization on the Earth, and then the outer space and universe to introduce the concept of the post-absorption and the conservation of energy. So in 1970, Harry Lever put forward the radical theory, which is a circumstance that in his
This is a lesson of technology. So.
Yeah, maybe there's something wrong in the internet.
Yeah, I think it's going to be
or maybe I could share the screen.
Yeah, why don't we do this? Why don't?
Yeah.
But
okay.
let's
just let me share the screen. Could you see my screen right now?
It's
yeah.
Share 1 second.
Yeah. Okay. Good start. I think we are still on the catalog, right?
Page 5.
Shaman, could you start it now? And
okay, we have already page 5. Yeah, in 1970, Harry Lever put forward the radical hypothesis of the complete urbanization of society, a circumstance that in his view required a radical shift from the analysis of urban form to investigation of urbanization processes. And in this book, drawing together the classic and contemporary texts on the urbanization question, it explores the various theoretical and methodological and political implications of the hypothesis, and it assembles a series of analytical and cartographic interventions that inherited spatial ontologies from the urban and rural, town and country, city or non-city, society or nature, in order to investigate the uneven imposition and the expositions of the planetary urbanization. Okay, next page, please.
Is it have some delay on the PowerPoint?
Yeah, it has some.
Okay,
Actually, yeah.
Don't worry, don't worry. Shaman, you would like to go?
Yeah, okay. However, if we take a look at outer space, we think the space junk could be a more serious problem. So the space archaeologist Alice Gorman takes the investigation beyond the Earth's surface and out into the near universe and put forward that while the orbital landscape contains the possibilities of greater complexity, it is also a landscape of decay. And the ultimate absorption may be the migration of satellite dust into the wider galaxy. Next page, please. So we could take a look at the concept of the absorption. It is a proposed geological epoch dating from the commencement of significant human impact on Earth's geology and ecosystems, including but not limited to anthropogenic climate change. Next page, please.
Is it really need to wait for such a long time? Sorry.
And then Liam Young, in his book Machine Landscapes, Architecture of the Post-Anthropocene, he said that we are seen to be living in a new geological epoch, the Anthropocene, in which humans are the dominant force shaping the planet. But this collection of species, however, is more accurately constitutes an era of the post-Anthropocene, a period where it is technology and artificial intelligence that now computes, conditions, and constructs our world. Okay, next page, please. So we should ask a question: how do humans prepare for the post-Anthropocene, and where do we go after we find the definition of this new condition? Okay, next page, please. The law of conservation of mass put forward by Anthony Lavoisier could be an answer. It states that for any system close to all transfers of matter and energy, the mass of system must remain constant over time. As the system mass cannot change, so quantity can neither be added or nor be removed. Therefore, the quality of mass is conserved over time. Then our research starts from studies on Earth and the conservation of energy. And when we talk about the Earth, the problems regarding to urban ecology cannot be ignored. Chapter 2 is divided into two parts, the problems within the Earth and problems out of the Earth. And Luca and Siron could introduce part 2.
I focus on the research studies on Earth and energy, and I divided it into 3 parts. into three parts, like the material, technology, and environment. And when we regard Earth as a material, we firstly think about the soil as a host environment, which has been used for the growth of bacteria and insects. As you can see, obviously the soil has different states which cultivated different life, such as algae, bacteria, plants, and animals. And for the bacteria in soil, it is the first life forms to appear on Earth, and it has various shapes and sizes that aggregate differently. And this is a catalog about bacteria, and you can see it has a great influence on our life, like dealing with the waste and pollution, and it can feed the world, also create some greener products. As you can see, it is our solution, and it's the traditional way, and it's some new way, and like this one is about the traditional life cycle about generating the fossil fuel for the human use. Um, next, next is about um, Next is about the farming, and the bacteria has the nature ability to do biological decomposition and create soil nutrition. So as for this part, so as for this part, there's an idea about a growth house in 1975. Uh, Sorry, for now it is page 20.
Yeah, it's a little bit late.
Oh, it's a delay, right?
Maybe Sean, could you please share the screen? I think my internet is not quite good today too.
Okay.
Yeah, please.
Could you see my screen now?
Still waiting?
Yeah, I think so.
Oh my God, I still have a delay too.
You can continue.
As for the food production, yes, as for the food production, I said before that the bacteria could do the biological decomposition and create soil nutrition. So as for this idea, a designer has a concept about a growth house. It is a self-sufficient and self-renewable dwelling, and it is made by clay bricks containing seeds. These seeds could create a source of food and be harvested and then eaten. As for the new solution, here is about a deeper sustainable method for farming. As you can see, it is a new package alternated that does not need to be recycled to still help the environment and at an even deeper level. So the second one is about use bacteria to do the bioelectricity and generate electricity, free electrons to for some other things. Also, it can create light, and when it is used with Arduino, it can also create music. And it can create greener products like the biofuel. They are combined, the carbon dioxide turns the algae completely into oil. It has the ability of photosynthesis that interact with humans. Human release the carbon dioxide and therefore oxygen is released. So the bacteria has its life cycle that it can create energy for human use, and then human release the waste. Then the bacteria could decompose the waste and feed back to the nature. Also, the ants and birds has its relationship with the soil, like the farming and hunting. And the second part is regard the Earth as technology, and we will focus on the round Earth and crystallization. So when we add some different materials into the soil, it will create different things. And it is a Chinese traditional way to make the soil into a building, and it's a really friendly environmental way to use it and use the structure to create to do the maximum weight with the minimum use of building materials. And it's also a clay brick to build a building. And for the new solution, we use there's a way of using biotechnological to mixing sand with the bacteria. So so the process is without fire, so reduce the carbon dioxide emission. Also, there's a self-healing concrete. It could release some stuff to close the cracks appear on the concrete. So the remote Earth, the technology itself could do a life cycle like this. As for the crystallization, it is a natural crystal in the nature, and it has a state change like the liquid to the solid, and it could be influenced by pressure, temperature, and some other conditions. Also, it's a way of make the state change. And when we add pressure to it, we will harvest the energy like the electricity from the crystal. And this is a case based on a context of an artificial saltwater landscape. And it will also generate electricity and activated the pumping system. Okay, the second part is we regard it as an environment, and we will divide it into three parts: the landform field.
Okay, the first part is about the landform, and it includes four parts: the karst landform, volcano, wind erosion, and the fluvial. Next, please. And in the karst landform, it's mainly about the chemical reaction, and that is the underground forms formed by the dissolution of soluble rocks by water with dissolving power. Next. And the chemical reaction in this landform is mainly about the material limestone and the water and carbon dioxide, how it becomes corrosion and sedimentary. Next, please. And this chemical reaction only need to react in the normal temperature and pressure. So in this page is about the creation of material, how the limestone were dissolved by the water, and it will create the physiognomy about like cast cave, sinkhole, break, and collapse funnel. Next please. And this one is about the generation part of material, and it will create like the stone bridge and the dripstones. Next please. And in the volcano part, it's mainly about the material and energy, and the volcano is ruptured in the crust of a planetary mass object, especially on Earth. Next, please. The chemical reaction started in the mantle rocks and finished in the ash dome. It's all like a kind of material transformation of the whole circle. Next, please. And there are three states of the. There are three types of the volcano. The first one is the eruption, and the next page. So, could you please go to the next page? And in this part, and in this type is the extrusion, and the last one in next page is the fusion. Next, please. And the volcano ash have a strong influence on the atmosphere called the Paso effect. The people in Romas have already used this volcano ash to establish to create the Roma concrete. In the next step, we might think more about the utilization of geothermal energy and the bacterial life circle around the volcano. Next, please. In the fluvial landform, it's more about the physical reaction. The water under the gravity erodes, transport, and accumulates the slides. Next, please. And there are mainly four type of the landform in fluvial landform: the gully, V-shaped valley, a predominant alluvial fine, and a fluvial delta. There are mainly four fundamental forces on Earth, and we will mainly focus on the gravitation and the magnitude. Next, please. Gravitation is a natural phenomenon by which all things with mass or energy, including planets, stars, galaxies, and even lights, and this whole gravitation was more considered like a network, which could be curved. Next, please. And this is a catalog of gravitation. Next page, please. This page is about its series, started from centered with its gravity of the center of gravity of a triangle, and finally come to the Einstein's general relativity. Next, please. This slide shows how the celestial body move around each other with a specific orbit under the gravitation. Next. Gravitation will also have strong influence on towards the creature, and especially it will influence the oxygen in plants to light the plants generate towards the sun, and then and there are also the gravitation from lunar creates the tides, and in the next page we'll talk about how we can use these tides. This is about the Cloris force, how the water streams forms of text, and how the atmospheric circulation infected by the Cloris force. Next, please. Just go through to the new solution. This page report is how the knowledge people utilize the tides as an energy. Next. This pumped storage hydroelectricity is about the method stores energy in the form of gravitational potential energy of water. Next, please. This is the Dyson sphere, the assumption of people think about how we can utilize the energy from the sun. Next, please. Okay, could you just jump into the next pages? These all cases are about how we can use the gravitation, like the lamp, how we use the gravitation to create electricity, to illuminate this, like illuminate using the power of falling sand to create light, and the marble, how we use the gravitation to create music by marble. Yeah. Next.
So the next part is about magnetic field, as the Earth itself is like a huge generator for the magnetic field, and its theory is all about electrical magnetic interaction, like generating the electricity. Also, it has influence to protect the Earth from harmful radiation and track the motion. Also has an interaction with ocean tides. It's also some in the nature that some animals could navigation from the magnetic field. Also, it do the direction and detection in the history, as it can generate electricity. Many stuffs had been informed. So it is about the electromagnetic wave that create many things like light, a microwave, and some X-rays and gamma rays. And it's a soft robot that truly be 3D pointed, and it could be controlled by the magnetic field. Also, it's a way of 3D printing it, and it is a life cycle that we generate the material from the sand and print the architecture. And it has been used in architecture simulation. So the third part is about digital simulation, and Xiaomeng will introduce it to us.
Yeah, so then we explore the methods of digital simulation based on previous research. And when we talk about the Earth, it should come to us that the Earth creates life. So the digital simulation methodology part mainly focuses on the rule-set behavior and artificial life. And we treat the material as host environment to hold different behaviors, which are soil, atmosphere, artificial environment, and vacuum, or outer space. Next page, please. Firstly, the soil. Soil could be as host environment for bacteria, plants, and insects, and each of them has different behaviors. Bacteria has many growth forms such as multiply and self-replication, and we can use the simulation ways both in voxel, such as cellular automata or game of life, and in particle in Maya. And also, soil is a host environment for plant, and we could use the L system to simulate the growth of plant. And when we take a look at the mushroom, it creates the bioelectricity for energy supply, and as the previous PowerPoint, we could see that they could generate music. And the soil is also host environment for insects, such as ants. So when ants search for food, they always find the fast way, which is utilized in ants colony algorithm. And the grasshopper plug-in Ethereum could simulate this process. Okay, next page, please. These are the simulation mentioned before. Firstly is the conveys game of life. Next page, please. Then is the L system, which could be used to simulate the growth of the plant. Next page, please. Then is a mushroom, which could create the bioelectricity. Next page, please. Sorry, next page, please. Okay, and this is the ant colony algorithm. And next page, please. Is there a delay?
Sorry,
page
it's
90,
about
page 90. Page 90.
yes.
Page 90, please. So when we take a look at the atmosphere, it is as a host environment for birds. And when birds migrate, they follow three different rules, which are the separation, alignment, and cohesion. And the board simulation in Touch Designer could show this process. Next page, please. Yeah, this is a basic rule of the board simulation. And next is about the conservation of substance. We could use Houdini with diffusion limited aggregation simulation to simulate the process of crystallization. Next page, please. And yeah, this is a process of the diffusion limited aggregation to simulate the crystallization process. Next page, please. Page 94. Yeah. So when we look at the outer space, it is as a host environment for the plants and a planet and space debris, and we could use grasshopper to simulate the magnetic field, and use Maya N particles to simulate the behavior of space debris. Yeah, this is Maya and space debris. Use Maya N particle. Okay, then Jadong could introduce
the last part is about problematic the scenario. Next. Based on the third part, we propose some problems corresponding to the bacterial working transformation. We came up 5 directions in the interaction between bacteria and soil. Next. The first is about food shortage. Bacteria can be used to make super trees to produce oxygen and protein to solve the food shortage. Next. The second is about biomass nutrients. Bacteria can have the ability to transform and store nutrients and minerals to solve the land aging and the lack of vitality. So next. The third is about can you go to 100?
Yes, sorry. My Wi-Fi, yes.
Okay. The third is about product packaging waste pollution. The deepest sustainable method for farming means a new packaging alternative that does not need to be recycled to still help the environment at an even deeper level. Next. The fourth is about the bacteria can deal with the pollution, like the biodegradation, the plastic degradation, and the carbon dioxide degradation, which can solve the waste products of human activities. Next. The last one, we think bioelectricity is more energy-saving and environmental-friendly way than the industrial power. We are thinking about why the biological power can replace industrial power. So next. So these are some of the questions that we think about the research as the starting point. In order to expand the research, we also introduce other thinking patterns. We determine the direction of research from the point of view of the problem. Can you go back to 104? 103. Yeah. The problem about Earth's surface, the impact of overexploitation of oil on geography and the rubbish mountain. The Earth's waste is buried underground, and the destruction of surface forests. So next. The problem of universe, the hazard of orbital debris and the space junk and mining space, and the difference between the Earth's internal internal and external environment and how to convert energy in different environment. So this is what we did. So thanks for listening.
Well, thanks, guys, for that. I mean, in terms of the first presentation, it seems like a good kind of overview of a lot of different issues. So I think there were certain things that kind of stood out for me. One was that you were conceptualizing the Earth, both the literal Earth in terms of like the ground and all the features that constitute that as a living system. And let's say from a more universal perspective, let's say the globe and the implications of, let's say, the energies that kind of keep it together and form. So I thought that that was interesting conceptually. I also thought it was interesting that you guys started to look at, you know, the Anthropocene and the post-Anthropocene strategies that people are using to describe this. On the other hand, unlike some of the discourse of those things, I quite like the complement of looking at something like Earth and seeing it as a kind of host environment with bacteria and all of these other kinds of elements that you guys were talking about. And I think the reason for that is that there is a certain abstraction that you guys can move through material in terms of bacteria, energy, seeing the difference between organic and inorganic materials and their codependency in some sense, right? So for example, when you guys showed Charles Simon's growth house, I think that that's a super interesting project, just from the perspective where you literally couple growing, like let's say the host condition of the seeds are embedded in the building blocks, and that you can think about how that somehow can transform. Now, this is a very old school kind of strategy that you would find very common in certain forms of farming. But this is done by an artist, architect, let's call it, dealing with concepts of earthworks. And I think the provocation of this, I think, is important in some way. It kind of, I think, speaks to the fact that these different elemental materials potentially could literally sustain life, could create shelter. It has a kind of complexity to it, which I think is interesting. Not so much because it's made of bricks and all of these things. I think you guys have showed examples that are much more generative and much more fused in terms of thinking about landscape and porosity and other kinds of features of the ground. Like when you guys were talking and the fluvial strategies and all of the kinds of things that you guys were looking at, there are a lot of things that are on the table which I think are interesting, and they speak to a certain way of somehow seeing the relationship between phase changing, what is the kind of seeds of life, how we interpret that. And in terms of like thinking about the Earth, I mean, I like even some of the thoughts you guys have had in terms of algorithmic translations. There are ones that are more familiar than others. So for example, like if we're looking at systems like reaction diffusion strategies, or if we're looking at game of life and different forms of voxel-based growth logics, I would see those potentially more engaged than, let's say, more traditional L systems, which basically kind of reinforce, for example, branching structures and things like that. Their L system is more linear in a sense in terms of how growth is. So you start, in a sense, branching, breaking, branching. So it's really like one line bifurcating into two or three, and then the same kind of process dealing with ideas of recursion, while some of the strategies that you guys were speaking about when you were talking about simulating fields, like the gravitational fields, the kind of space junk, all of these other kind of things, I think naturally bring in dynamics as a feature. Now, the difference between some of the techniques that people have used in the past and some of the things that we could potentially do is to see this very different from, let's say, what a morphodynamic process is. So in the 90s, for example, 2000s mostly, people were using, fluid generators in a sense to kind of shape form. This was quite common. As long as you don't think of it literally as form, like in terms of shape, and you see it more like formation, like a sand dune, how a sand dune will change, I think that becomes an interesting way to see the relationship between things. I liked even that slide that you showed, like sand, earth, in terms of what we would call soil and other things, and spoke to some of those different things, because in some ways, that's all part of how we start to see these kind of particulate matters. And, if we're simulating matter that's inorganic or organic, or if we're simulating, let's say, for example, some of the swarm behavior and voids that you guys are talking about, it becomes interesting how we can use maybe some of the abstraction to be able to communicate more of a hybrid thing, meaning that we're not trying to represent, let's say, just a pure simulation of, let's say, how sand moves, but for example, when for example, you have sand dunes and stuff like that, Frei Otto was doing a series of research, for example, of the angles of inclination. There are specific angles in sand dunes that kind of keep dunes together, and it's based on the size of the particle. And if you have more coarse sand, you can have more inclined angles and things like that. So depending on where you guys find more interest in, I don't think we need to select something yet. I do think some of these interests in game of life and some of these other simulation methods, I would encourage you guys to start to look at that. It seems to me growth is one thematic in the simulations that we should look at. And it seems to me like in terms of growth, it's a kind of what we would call a seeded strategy, which is not one growth point, but multiple growth points, and potentially look at how the environment is kind of influencing different rates of growth or different morphologies of growth. So I think that would be an interesting way to maybe set up some of the, early kind of studies into that, so that we can start to develop strategies of that. The other one is more about, I think, somewhere between, your ideas of gravity and force, and how that somehow really somehow engages maybe some of the stuff that you guys were doing with swarms and things like that. So like Mustafa would be talking to you guys about voxelization versus agent-based kind of strategies. It seems like there's two paths, and I think they're useful. One is more environmental and one is more kind of genetic. So the growth logics are much more genetic. And I think the agent-based strategies and the ways that you guys would be using it potentially here would be much more environmental, meaning that the agents want to do something, but the environment is also influencing that, and how does the agent negotiate? So these would be like some basic starter strategies for maybe thinking about this. I like your concepts of energy. I think some of them are more specific than others. So for example, when we're talking about the kind of water generation of energy, it's definitely very clear in slides like, if you go up to slide 56 or 60, what is hold on, like 56. You know, when you start to see these implications of morphologies that are being shaped and somehow is using the ground as a kind of interface for flow and all of these other kinds of things, it's useful to kind of consider those things. But we don't know exactly what scale that we're thinking about. In the beginning of the project, you guys make the implications that in some ways the globe is your site, right? Like in some sense, it's almost like taking the logic of the fact that we are terraforming the world, that actually the world is the site for the project, and not potentially not even the world. It can be space, and the idea of harvesting materials and all of that. I think all of this information is interesting. I think the way that you approach it, I don't think we have to take too many decisions there, but I think that there are ones that are more speculative than others. So I would just try to encourage you to think about the fact, like, when we mean sustaining life and we are looking at an earth strategy for that, I think your attention to bacteria and growth, and also your strategies that we're looking at ideas of crystallization and how we can do that at multiple different scales, would be a way that I would approach it. So for example, if we're looking at this scale in particular, you know, we're still looking at earth and water and nutrients, but we're zooming out to a scale where the implications of how and what we're simulating would be at a very different resolution, right? It's very different than taking a sample of soil and looking at a plant grow. So what we would be simulating would be very different. Does that make sense?
Yes.
I mean, I quite like the way that you guys have brought all of this stuff together. There are certain things that I think maybe things that maybe are less interesting. So for example, when I see slide 65, it's not that I dislike this kind of ideas of harvesting, but this also speaks to not something that's really, at least in my understanding, very earth-based, right? While, let's say, slide 66 is a technology of really capturing, let's say, water for redistribution through using the mass of let's say, the ground in that sense, right? Now, for example, if we're talking about water, we would be sort of looking at it in terms of moisture, if we're talking about it in terms of the ground, right? That's the difference between sand and some of these other kinds of soils that we're talking about that can grow different things. And you guys talked about algae and a lot of this other stuff too, which I think is useful as well. I do have to say, I know Ecologic Studio speaks to a lot of these kind of things in some ways, in terms of like literally using algae. But I think that there's some very important differences, right? So this project, for example, that you're showing on slide 25, all of these morphologies are really not based on growth. So these morphologies are really like an architecture, which is really like a scaffold, and the algae is kind of plugged into it, right? So literally what Claudia and Marco are doing is that they have this 3D printed form, it's got a series of holes in it, and they're squirting the algae into the 3D print, right? It isn't really a scaffold for growth, meaning it's much more representational of an idea than the idea itself in terms of how we would approach some of these problems. That doesn't mean that we wouldn't look at stuff like 3D printing scaffolds and things like that, but I think we would do it in a different way. One other thing that you may look at, you guys did show an example of sand-binded bricks. And one of my ex-students' wife developed a bacteria to basically use just sand and this basic bacteria strategy to bind bricks. And she has a company now, and she was featured in a lot of things, but she's been working on this thing now for 10 years. She was studying in Sharjah, and I think if you look at this Biofabricate conference, you will find her. I will find the things that she's been doing, and I will try to post it on a Teams channel that we can set up so that I can put some links and things like that for you guys. Okay. But I think overall, that there's some interesting stuff. So I like the presentation a lot. I would just try to look at this stuff a little bit more directly and try to organize the material. So for example, I don't know how many slides we have right now. 140, which I mean is great. But I think like we can start to try to take some decisions about certain things that maybe are interesting to kind of have in terms of just like the language, but how we start to sharpen up some of these things. Some of these things are looking at the spatialization of the ground, for example, like when you show me the caverns that have been crystallized, or when water is eroding different kinds of elements. So there are moments of kind of subtractive strategies, and then there are others which are additive. So I think we can start looking at these things maybe in different ways. And as soon as we really start to get a handle on what is it that we're really trying to simulate, I think it'll become more interesting to have this kind of resource of things. Now, I don't even know if you guys are designing something on planet Earth, or you guys are going to do something in space. And even that, I think, is okay to leave open for right now. As you guys are developing strategies, I think it's good to have a certain openness. You guys saw Apo's project?
Yeah.
In one sense?
Yeah, exactly, the space oddity.
Yeah. Which I think is, it's a super interesting project. But at the same time, I also think like the time that we did those things, I think the whole notion of space and the kinds of conversations of what people are trying to do. Like I listened to a podcast today of Elon Musk and his whole concepts that he's interested in space are very different. One of it obviously is just like literally an economical model to make space tourism more possible. But the other one has to do with extracting of materials. Particularly because he's in the business of energy much more than he is in the business of cars and rockets. I think some of the things that he's interested in is in capturing energy and capturing resources that are maybe not so available on Earth to power, let's call it a more electric way of thinking about generating, energy. So I think it's interesting to maybe, if you're interested in some of those things, just to try to go a little bit deeper into some of the contemporary ways that people are looking. But I definitely think Apo's project is an important one because in some ways you see the way that we were working. In principle, in the digital world, it was mostly particle strategies, things like this, which had certain limitations, right? Because they were primarily driven by attractive and subtractive kind of void formers and things like that. When you see the models, I think you see something else is happening, which is that we designed the particle, meaning that the particle itself, we were using the spherical kind of packing strategy, which I think is very common, but to help with its self-organization, we introduced vectors in the sphere to be able to have different properties of connecting and disconnecting. So for example, when you are in space and you're dealing with orbital forces and things like that, that self-organization is driven by the environment. So based on what we consider environment and based on what we're considering in terms of growth, and slowly when you guys start to think about living, I think it's interesting. That's why I think you should hold on to this idea of the growth house in some way. It doesn't have to be literally about planting seeds, but I think it's something interesting to think that the architecture itself becomes the infrastructure for growing. It could be food, or it could be something else. So I think we can start to think about even a kind of hybrid about what we think living is. You guys have showed a certain diversity in terms of environments, which it would mean something radically different if we were in space, right? Than if it would like if we were in an extreme climate like the desert or in Antarctica. So that's why we don't work with sites at the moment or any of that stuff. So try to look at the relationships of what you think living is, and let's try to take that the next step further. The thing with bacteria is if we are talking about living, we're talking about living from the bacteria's perspective and what those bacterias and cultures can create for us. So I think that this is also very interesting because even, let's say, our skin is a host to all kinds of bacteria. It's kind of like a soil for very different bacteria, some good, some bad. But this is what this kind of deeper ecology actually starts to offer us. So I think the Ecologic Studio strategy is a little bit more traditional because it sees architecture as a form that then gets populated. I would really like you to think about architecture as a process that over time is changing. And I think because it's a process and because it's changing over time, the idea of infrastructure, the idea of landscape, the idea of forces, I think are very complementary to understand what change means. It's not a kinetic change that means that it has one state or another. It's a much more symbiotic relationship to the environment. So I think it's a good start. I would explore a little bit deeper some of these things and try to see which one of these things is starting to give you something also that you really haven't seen before. I think in some ways, like that doesn't mean not to do a space project. I think the question would be like, if you are doing a space project, what would be the fundamental things that you're trying to do with this project? What's it motivated by? One of the challenges that I would just say to that is a lot of people are spending a lot of money to do things on Mars, for example, right? This is very common these last 4 or 5 years. But realistically speaking, Mars's climate is much, much more complex. I mean, in one sense, not so complex, but much harsher to create and sustain life. That one of the critiques about this, and I share it, is that we have so many environments on Earth to prototype and test these things. You don't need Mars in some sense. We have all of these kind of extreme elements here on Earth, and the problems that people are usually putting forward to kind of make moving on Mars important are probably more urgent for the people that are here on Earth now, right? So if we can develop a more self-sustaining, extreme environment, living architecture, if we can do it here, we would probably be much better at helping people. So just keep that in mind in terms of how you're thinking about things. I don't want to influence you too much. I just want you to really engage a bit deeply in terms of some of the implications. Conceptually, I like the way that you're thinking about it, and I like some of the examples. So try to do a next round to try to consolidate a little bit after this conversation. and we continue with it. Is that okay?
Yeah.
Yeah, okay. Thank
Okay,
you.
sure. Thank you.
All right, guys. Very good. Okay, so we did Earth. What should we do next?
Can I go next? Water?
Earth, water sounds good to me. Why not? And as you're saying that, Tyler, I'm going to get a glass of water just to be inspired by this.
Daphne, maybe you can share the screen.
Okay, guys.
Okay. Maybe I will share the screen.
Give me 1 second, sorry.
Okay. Okay.
Great again. Okay, so we are water theme again. The UG Tyler online me. We started creating this whole water catalog as we were discussing, and we'll try to present the basic directions of our research. The water as material, water as technology, and water as environment. Like it's well known that water has a very strong cultural impact, and it throughout all these years it signified many different things, and it played a very important cultural role across different societies, across different social activities like therapy, social life, religious, meditation or recreation, agriculture, transportation, exploration and trade, and that's it. So, as we all know, the whole surface of Earth is like 70% of Earth's surface is water, and 96% of water is ocean. We started exploring water as a material, going through the chemical composition, then seeing the special properties and effects that water has, the phase changing, diverse properties throughout the phases, physical properties, patterns, and some ways to harvest energy from these water properties. So first of all, this is the chemical composition of water, as we all know. So 2 atoms of hydrogen, 2 molecules of hydrogen between 2 atoms of hydrogen form with 1 of oxygen form the molecule of water. And the water has some special characteristics which make it so special, comparing it to the rest of the fluids, which is the boiling point and freezing point, which is actually what allows life on Earth to exist. Heat of vaporization, density, which is why ice floats, basically. Viscosity, which is pretty high. The cohesive forces that can that we see in water, which also are responsible for effects like the stretched membrane effect. Adhesive forces, which are the properties that are responsible for the capillary action, and which helps plants to do photosynthesis, and surface tension, which allows the drop formation through the strong bonds that are created between the surface molecules of water. And that pH is 7. So Tyler, you wanna?
Okay. Next
These are the
slide
three
is
different phases of water, as we know: gas, liquid, and solid, steam, water, and ice. Accordingly.
So there has some like interest fact as water's nature behavior. You can go next slide. Yeah, with different phases because each phase has their uniqueness in terms of the structure, the chemical structures, and lots of energy consumptions. These are some interest facts throughout the research. From lots of different aspects. Okay, go next. Okay, first about the volume expansion, because when water turns to ice, by the research, it's gonna expand 7% of volume because of it's due to the chemical structure. When it's liquid, actually, each molecule is actually twisted together. But when it turns to ice, so like the diagram underneath, the middle one is actually the structure expand a bit to let the stick between the atoms to expand a little bit for a more solid structures, chemical structures. So that's what ice chemical structure looks like, and it's quite unique, and it's naturally like kind of a natural behavior between liquid and ice. Okay, next, yeah. And about the bending also is another interesting fact that because water is a polar molecule, so it creates positive and negative electric charge. So when we have other magnetic like attractions near the water, so it's get bending, like the picture shows. And also with gravity, and when we pull the liquid out, so it's naturally create a curvature, like the picture below shows, because of the electrical attractions and compositions of the chemical structure. Okay, next. Okay, and the thickness is actually quite important fact. Because later we'll explain, there has one example is very interesting and quite important. And the thickness of the water, because of the hydrogen bonds, so it creates extraordinary thick fluids. And yeah, we will explain this later as an example. It's kind of simple. So when the molecule bends together, so it creates naturally thickness. Yeah, next. And about the shape, one very kind magic of the snowflake. You can go next page actually. There has lots of documentation through history. The first people who documented different shape of the snowflake is Bentley, and the reason why the snowflake is getting different shape is due to the temperature changing, and can you go to previous slide 6? Due to the temperature changing and like the second graph explained, when ice crystal that make up snowflakes are symmetrical, because they reflect the internal order of the crystal's water molecules as they arrange themselves in predetermined space, known as crystallization process. So this process is actually affected by the temperature which a crystal forms, and to a lesser extent the humidity of the air. So this is two key factors. One is about humidity, and another one is about the temperature. So like they suggest like 23 degree it's gonna create different shape with 5 degrees. Yeah, next. Next page. Okay, so here we found some interesting documentary about the ice sublimation. It's like it's kind of a lot of quantity of the ice snowflakes, so it's kind of cluster behavior by experiment. When the ice sublimated is actually because of energy changing due to the vibration, so the form is actually continuously like moved because of that process. And another interesting fact as a behavior of water of ice, let's say, about the formation is like when the spike is not only go down because of the water drop, but it also can go up because of the pressure. Because when water transfer to ice, it's actually from outside to inner side. So when if we have a volume of water and the temperature drops, so it's gonna create ice from surface. So the inner part is still liquid, but because of the expansion of the volume of ice of the 7% or 9%, sorry. So the inner part get more pressure than outside. So at the middle part, the pressure will let the water goes up like the lava effect kind of. So that's the reason why it can grow up. Okay, next page. And this is experiment of this effect. It's kind of interesting, so we put it here to get a visualization about it. Okay, yeah, next. And about the transparency, because the ice formed by temperature super cool process, and the transparency is affected by bubbles and purities. If the water is more pure, then it's gonna create a more crystal-like transparency. But if the temperature drop too fast, and some ice bubble will stuck inside the ice, so it's gonna create a less transparency about it. Okay, next. And we find another experiment created by NASA, because we find buoyancy or fluidity is quite an important fact of water also. So we imagine what if water without gravity, so what's it gonna look like? And because of the thickness of chemical structure, it's gonna hold together and create the fluidity because of the movement. Yeah, like the video shows. Okay, next. And another important factor is the desalination, because now as the suggestion as the previous slides, we know like 71% of Earth is ocean covered, and 96.8% is about ocean water, salt water. So if I think this is a very common argument, not argument, like a common intention to how to use salt water for our daily life. So the traditional way is about this diagram, like they basically use the evaporation process to purify the water step by step. But this has one problem, is because we need to heat up the salt water to purify it. So it's gonna have lots of energy consuming process within it. Okay, next. So nowadays, actually, because of technology, we have two very popular process to purify the water. One is called reverse osmosis. Basically, it's used a lot of permeable membranes to purify the water. And okay, next. And another one is about the material graphene. Graphene is not it's pronounced right. Because the natural structure of because of its natural chemical structure, it can allow only like the water chemical structure to like the molecule to pass it, but stock other like bigger like dots or some other stuff to pass by. Okay. Next.
Yeah, back to analyzing the basic water properties. Two different flow types it can be examined. The turbulent flow and the laminar flow. Oh my God, I have this. I had to change these names. So the laminar flow is a smooth flow with particles in distinct layers, while turbulent flow is has a chaotic behavior. Particles are diffusing. It's very, very sensitive, and it creates eddies with high vorticity. The flow is generally affected by the geometry, velocity or flow rate, viscosity of the fluid, and pressure. So that's why, for example, we can always honey drops with a very smooth way, because it has very high viscosity. As we can see, the smaller is the Reynolds number, we can know that the flow is laminar. So after that, we just thought that we have to look at different patterns that can be created by water, regarding either in the water surface by different currents and tides, or in the sediments and in the subsurface by waves and pressure. So these are the main ways that we can find that to harvest energy from water as a material, like through erosion, by extraction of sediments, deposition, by creation of rocks and crystallization growth, transportation of sediments, current waves, vaporization, pressure, turbulence, and microorganisms. So in the next part, we're going to go through water as technology, water management infrastructure in ancient times, or water management infrastructure more contemporary, and some harvesting water properties that could provide us with some, we can see some case studies there. So water and flood management is divided in 6 parts, like measure and analyze, collect water, store water, harvest energy from water, desalination, creation of fresh water, and protection from flooding. So first we had the example of nilometers, which were very structures in very significant structures in Egypt that trying to measure water and predict the floodings and also predict the agriculture for a year. The Qanat system, which was a transfer and distribution system in Syria, which managed to transfer with minimum evaporation and that simple way of creating channels underground. Aqueducts, these megastructures Roman Empire created, which were basically for transfer of, which used basically to transfer water. And then step wells in India, which were used to store water and which were also very important about the social life of villages. And also they had some religious aspects with this example. This example of step well has a temple over here, and it's very close to I think a royal temple. Yeah. So these are the three different types of step wells. This is very interesting because it creates a very vibrant social life around the water, with multiple people being able to perform activities like bathing or anything. And this is the most common example of step wells, this is very common even in the smallest villages, and are created through a stepped corridor and between two parallel linear walls, which ended up to the reservoir of water. So aqueducts used to transfer and distribute water, step wells used to collect and store water, providing at the same time social gathering, and they were called also like women's spaces, and nilometers, which were ways to predict, to evaluate water and to predict floodings, and qanats, which were methods to transfer and distribute water. So in terms of water infrastructure, also we have the air wells, which were used to collect water from the atmosphere. So this is an example of it's completely passive and it requires no external energy source. But unfortunately, this specific example built in 1930 in France produced no more than a few liters of water per day. So this is a visited example of Warka water in Warka Tower in Africa. Was used to, it works in the same exact way, but using the net, a polyester net, to collect water drops from the atmosphere through gravity, condensation, and evaporation. With this structure, they calculated that they could collect around 40 to 80 liters of drinking water every day, according to the weather conditions, of course. So this is the net that is collecting the water. I think this example is interesting because it also allows the creation of different prototypes of worker towers, and it creates also a social life around it. So back to some more, a more brutal example. Yuji, you want to? Yuji?
Yeah, I'm here. So another way to store the water is the dams. This picture shows the largest reservoir in America, the Hoover Dam, which is constructed in 1936. It's also used for harvest energy from the water and manage the flood. It's very huge, about 87.5 million cubic feet concrete, and can output 4.2 billion kilowatts electricity. Next. So the method of them is to store water and raise the water level, and the water flow drives the water turbines and rotate
to generate electricity. Although the dam is high, sorry, the previous one. I didn't finish. Yeah, although the dam is a high efficient product, the dam is also against the nature, which is a barrier and stop or restrict to the flow of the water. It can damage the ecological balance. Next. This is a famous irrigation system in China, which is treating the nature in a gentle way. It's not against the nature, it works with the nature. So this name Dujiangyan was constructed in 2000 years ago and it's still in use today. It divided the Minjiang River into two parts. The one of the parts filter the sediment and flow into the Chengdu Plain, where people can use the water gently. Without Dujiangyan project, the floods will commonly happen in Chengdu Plain. Next. The irrigation system is composed with three main water projects, the fish mouth, Feishayan, and Baopingkou. And also it plant many trees to stop erosion. The first project, fish mouth, is nearly 1 kilometer long dike made of large bamboo cages filled with stones and placed in the middle of the river. It was designed to divide the Minjiang River into two parts. One is used for drain of the flood waters, and the other part is used in irrigation. And the second project, Feishayan, is mainly works as a flood discharge, desilting and regulating the water flow. And the third project, Baopingkou, is a diversion project. It works as a control valve. It can control the water flow of the inner river automatically. Next. I would like to introduce the method of Feishayan to desilt. It is to create a water turbulence by creating a curved route for the water and building an underwater terrains. When the water flow through this man-made curved band, the water level of the concave bank is lower than the convex bank because of the centrifugal force. And then the different heights between these two banks produce the pressure difference, which causes the water turbulence. And it scores the convex bank and brings the suspended sediment from the water of bottom to the convex band. So the top of the water becomes clear. Next. When the water flows through Feishayan, it creates a spiral flow due to the curved route, which remove the sediment and make the top clean water flow into Baopingkou and survives for irrigation. So it will help up much sediment in Feishayan. And in the low-level water season, people need to clean the sediment in the river once a year. Next.
Yeah, we couldn't talk about water without looking at the delta works and the flooding protection system that kept actually a whole country into existence. For more than 40 years, Delta served as a construction site which challenged engineers to invent tools, vehicles and materials, which also formed the basis of the Netherlands' strong position in hydrodynamic engineering. The Dutch culture of planning originates in this struggle against water. So in the first plans, they were considering of shortening the coastline and turn the delta into a group of freshwater coastal lakes. Soon they realized that creating such a large freshwater lake would have caused major environmental destruction with a total loss of saltwater ecosystem. And consequently, this could cause a great disaster. So government agreed to build a very complex system of storm surge barriers. So this is one of the largest system of this, which is a 9-kilometer long storm barrier. okay, it's a very complex project, but I think the essential part from this is that it can at the same time it can at the same time block the storm and but also allow the sea to come inside. So they can adjust this. So this is a mechanism of dams and currents. And this is one of the most recent infrastructures that were created, the Masland Buried, which is quite also a huge infrastructure, almost as long as the height of the Eiffel Tower and weighs 4 times as much. Again, a movable infrastructure. Then I think that what we could get from this example is just the whole picture, to understand the scale of this project, and that through studying the flooding and through their struggle to balance between their existence and the existence of their ecosystem, the data that were addressed a variety of solutions, responding to its threat in a different way. So it's a very complex system of slices, dams, and storm barriers. Yeah, this is some very basic flooding control. Yeah, to sum up, this is again the work at our with harvested water, the irrigation system of Duichi Young, which managed the flood and irrigate, and created an irrigation system, and the dams which stored water, and managed to create hydroelectric power. And then the Delta works which kind of combine all these things, except from water collection. Then we have some basic examples of how to harvest energy from water properties. So this example from MIT Self-Assembly Lab shows how to harvest wave energy through deposition in order to grow islands and artificial reefs. This is a very passive example. There's no real intelligence in that, but I think it's interesting how with very minimal in a minimum way you can create something new. So this is an example that shows how to grow crystallization through salt, using the process of water evaporation. And then we have some examples from the MIT Cancer Research Lab. So Institute, where they use water evaporation in order to lift almost objects that are 10 times the weight of this object. Again, the WIS Institute, where they used water pressure and they programmed the material to respond to this pressure, creating an artificial muscle skeleton which could grip, lift, and twist 1,000 times the weight of the object. Then, how we could use some microorganism in order to get an outcome like bioluminescence, or to use algae in order to get some alternative energy or to use it as a mechanism of growth. Ola, you wanna?
And this one is basically using the different temperatures in water in the ocean, where the surface of the water is warm and the deep sea under the water is cold. And what they're offering the OTEC, ocean thermal energy, is they conserve these different temperatures into electricity, which is very promising. However, all the examples that we've seen online to our research is big plants. So we're going to see how this could be useful to and how we are going to move forward with the brief and the project. Next. So for the third part in our research, we're framing water as an environment by exploring the human settlements on water and which water bodies they live on. Next, please. There exist 5 water bodies in the world where most of what we found, a lot of the settlements are located either on lakes where fresh water is harvested and on the sea. Next, please. So this map shows that human settlements that exist now on water are found in different parts of the world. And as we go through these case studies, we will find out how they all share the similar cultures that was enabled by the water and its environment, regardless of their location in the world. Next, please. So for our first study, located in Nigeria, the Makoko Lagoon, it's situated on the ocean with an area of 1 kilometer. Next, please. It is considered as an informal settlement on water, first constructed by fishermen who came from Benin before it turned into a safe haven for African immigrants. Next, please. So these homes are built on stilts with inhabitants of a population of 250,000. Transportation here is mainly on boats, and their main source of food is harvested through fishing. Next. So the second case study are the Bajau people, sometimes known as the sea nomads, who lived in the ocean for more than 1,000 years. On small houseboats that float in the water off Indonesia, Malaysia, and the Philippines. The total population of these Bajau people across the ocean is around 1 million. Next, please. So their homes and schools are mainly constructed on stilts scattered on the ocean. This kind of construction helps to accommodate to the changing water level throughout the year. Next. The transportation here in the settlement is mainly by boat and also a few bamboo pedestrian bridges connecting some house stilts to the other. The Bajau people are among the most accomplished divers in the world. They collect their food by free diving to depths of more than 230 feet. They have no wetsuits or flippers, and they only use wooden goggles and spear guns that they make themselves. And sometimes they rupture their eardrums at an early age to make to be able to dive in deeper in the sea. They fish sustainably by making fish traps made of wood and bamboo, and this helps in the preservation of the coral reef existing there. Next, please. So we move on to another form of settlement on water, mainly by the port of Hainan in China. It is a harbor for Tanka people who lived there for generations. Its total area is 24 square kilometers with only more than 100 people. Next, please. So the name Tanka refers to boat dwellers, as in the people living on boats. Their origin is uncertain, but they are considered to be outcast from the land in the past. Next, please. So they are known as the sea gypsies. Their homes are connected to their fishing nets, where their lifestyle is mainly comprised of fishing. Next, please. So moving on to another water body that humans have settled on, the Tonle Sap Lake. It is considered to be the largest lake with an area that fluctuates during the seasons from 2,500 kilometers squared to 25,000 kilometers squared. It has a population of 4 million people living around and on the lake. Next. So the main characteristics of Tonle Sap is the ecosystem generated by the 2 rivers that feed it, the Mekong River and the Tonle River itself. So during the dry season, between October and April, Lake Tonle has very small dimensions and only 1 meter deep. But during the season, the rainy season, they carry more flow into the sea, then it is able to absorb more water. It returns to the mainland and sits on the Tonle Sap Lake. With this process, the lake expands and multiplies by 10. Next, please. So the overall population is scattered around and on the lake is 4 million, where 1 million of this population lives on a floating village. Next, please. So because of the floating season, the typology of the homes on stilts were used to accommodate the different water levels. You can see how these indigenous people constructed their lives around the seasonal environment instead of imposing. So you can see during the dry season, the houses on the left and their stilts are shown, while in the wet season, the houses look like they're floating on water. Next, please. So there are 2 forms of transportation used in this area. During the dry season, the water level is low, which creates ground and walkable roads, whereas during the wet season, the roads are submerged in water and only boats are used for transportation. Main food is fishing and agriculture on water. The flooding of water and the rainy season enabled a specific culture where the festival lasts 3 days and commemorates the end of the country's rainy season, as well as the change in the flow of the Tonle Sap River. Next, please. So here, another form of human settlement on lakes. It's in Ganvi, Benin in Africa. It's known as the Venice of Africa, with a population of 30,000 people. Next, please. So the lake is only 1 to 2 meter deep, which enabled the inhabitants to make artificial land by bringing the soil from the land. Next. These patches of land are used for agriculture to keep to keep domestic animals. The houses, again, here are constructed on stilts, the same typologies that we've seen in other areas of the world, continents of the world. Next, please. So, similar to other cases, the transportation on boats. Sorry, is this, okay, yeah. The transportation on boats and their main source of food is from fishing and using artificial lands for agriculture. However, one of the challenges that they've been facing is the invasion of a plant that is preventing them from fishing. But recently, this type of plant was found that it can clean up water from oil spillings and chemicals. So as you can see, they use the resource, what the water is giving to them as a resource, and they call it green gold now. Next, please. So this is another case study on the lake, very small community or village. It's located in Thailand with a population of only 1,685, and the area is less than 400 meter long. Next, please. The typology of their homes are again house on stilts. The distribution, next slide, please. So the typology of their homes are again houses on stilts. And the distribution of the village itself is along a main curved line. Next, please. So again, we see similar culture of fishing and transportation with the other previous settlements. Next. So finally, the settlement is located in Urus, Peru, where floating islands on the lakes are on the lakes, and its population is around 1,200 people. Next. The islands are located by the shore of the surrounding reefs. The reason behind why they've settled there is that they were a threatened community in the past, where there was invasion forced them to live on water. The idea was constructing a flexible island or flexible islands that could be moved whenever they were threatened. Next, please. So basically, these islands are made of reefs and they contain no soil. The reed has a high buoyancy due to its environmental conditions. It grows on the banks of the Titicaca lake. The base in contact with water ends up rotting, and these gases contribute to the floating of the structure or the island. These organic islands, up to 3 meters thick, they need constant care in renewing their dry braided plant to maintain their integrity. Most islands have watchtowers where visitors and residents alike can catch a more aerial view of the whole area. So they also collect the reeds to build their boats and small rowed and straddled fishing vessels. And this tradition and lifestyle has been there for at least 3,000 years. Next, please. So here it's an overview of all the cases, and we categorize them according to scale in reference to their population. The largest on a lake, 4 million people, and with the smallest in the sea in Hainan Port with 100 plus people. Overall, the water enabled similar lifestyles and typologies, even though these settlements, again, are located far from each other in different continents, Asia, Africa, South America. So what we learned from this is that the potentials of creating a life on water is there, and it existed for many years and still exists to this day. And the potential working along with water and its conditions without imposing on it. Next, please. However, there's a dark side from misusing the resources there, or misusing or like treating nature in a bad way, created a lot of challenges in these settlements, from water pollution caused from sewage to threatening of the coral reef ecosystem, to overfishing because of the use of unsustainable way in fishing and the change of quality of water. Next, please. So to sum up, and basically the main themes and derived from water as an environment are the human settlements, the reef growth, and pollution. Next, please.
We started considering water, what would mean water as threat for our civilization. So we have some different problematics that are water scarcity, sea level rise, floodings, and erosion that come. All these come from water. So water, we can see in these two maps from NASA, water scarcity level in 2007, and the water scarcity in just a span of 7 years. At the same time, we can see how human infrastructure could affect and accelerate water scarcity, and also be the reason of conflict, like this huge dam between Ethiopia and Egypt. At the same time, climate change causes the rise of the sea level. And in these diagrams, we can see clearly the effects of this. Erosion is an issue that comes also from this from sea level rise, and we see more and more villages and houses disappearing from falling cliffs due to erosion. So we considered, like, what if these different approaches towards erosion and flooding seems to not to offer, not to harvest this energy that comes from the waves and the ocean currents, and at the same time to destroy an ecosystem. So these are the three basic strategies that we follow as civilization, like filling with sand, concrete walls, and breakwaters. So what if we could turn these threats into our allies? What if we could extract energy from water as matter, balancing fresh water with seawater, or balancing water with land? These were the main strategies that we tracked as methods of extracting energy from water. So erosion and deposition could be considered as strategies of artificial and self-constructed topography that gets shaped from the force of currents and protects the coastline at the same time. While a strategy of salt growth or algae growth or microorganism growth could help us in a strategy of providing more fresh water and somehow thinking of decreasing the seawater and making creating more fresh water probably. So these were some initial thoughts regarding we started creating some simulations in different frameworks, simulating frameworks from Houdini and Maya using vector fields and particles in Maya. And these are some basic thoughts regarding interacting with water as material. How can we mine data from water, either by read water patterns with computer vision, or by censoring surface or subsurface temperature, or by collecting ocean data and weather data and predicting weather probably. And at the next phase, we could see how how we could enable like a user interaction with water. But this is a second phase of that we could consider. Yeah, that's it from us. Thank you.
Okay, guys, thanks for that. I mean, I think you guys also obviously have shown quite large array of things. I think if you just maybe launch the thumbnails of the slides, I think it would be helpful. I mean, from my perspective, I think that there are certain things that you guys showed that seems to me have like a lot of possibilities of interpreting. I mean, I quite appreciated a couple of different threads of research. I have to say, like the real material behavior, I mean, thinking about the matter of water and seeing everything from like snowflake generation and its relationship to environment and temperature. I think that there is a lot there that one can somehow explore, aside from the kind of material behaviors that you can see in the different formations. I also think just even if I was taking it from a conceptual approach to think about an architecture from a generative perspective, that could basically almost have infinite variability in some sense. At some moment in time with my brother, we got a little bit fascinated by some of these kind of things. And I remember when we were doing some stuff for Archigram, we did have an interest in some of this, but it was at a time where honestly we didn't push it as far as potentially we could have. And I think there's something quite beautiful about the way that, you know, surface tension in water influences formation. Temperature creates all kinds of aspects, from atmosphere to hard, from opaque to transparent. So there is something about the direct use of water as a material, which I would encourage you to really push. The examples that I showed you in the presentations, like Gaetano Pesce and things like that, or Heinz Isler, those were kind of very, I almost want to say very literal examples of basically freezing a house or creating a shelter like an igloo by just basically using a kind of wet fabric. So I think that there's a lot of potential there to think of an interesting way of doing digital physical experimentation. And I mean, the more that I've been thinking about the studio, it used to be a way that I used to talk about this stuff back in the day, but I think thinking about it as digital materiality, I think is a good way to express what we're trying to do. It's not just about simulating material, but it's also trying to utilize the kind of digital properties of our platforms and to see how we can deploy that in a material way. So I think it's more about trying to experiment, even with very simple kind of even home experiments, to understand behaviors and to see how that can influence the way that you think about setup and the way that you think about, you know, the generative possibilities of different phase changing and different kind of environmental kind of conditioning. I think the other aspects that I made some notes here that I thought were interesting. I mean, aside from those material things that we were talking about, like stickiness and shape, was the aspect of the ritual and the kind of social and more the kind of human interfacing with how those things have a very direct engagement. So you guys showed everything from kind of step wells and things like that, which are kind of architectural byproducts, which are really like moments of convergence of how like people are, you know, because of the survival and necessity, are somehow exploiting the kind of architectural instrumentation in some ways. And I think that there's something about looking at what Ulla was presenting in terms of the architectures that are, you know, shifting that relationship, right? The step wells are really a consolidated amount of water, and the architecture and the urbanism is the dominant fold. When you shift it to the opposite, meaning that you change the proportion, and you start to see these architectures as islands and little ecosystems within a water body, I think it would be really nice if you guys can find a diagrammatic technique that can somehow start to pull these worlds together in an interesting way, because I think our definition of architecture, if I take your presentation directly, sits somewhere between, let's say, the aspects of harnessing water, which goes into the conversations of the fresh water versus salt water. It goes into some of these different kinds of instrumentations of doing that. Now, if that's like a Turkish air well or other kinds of examples like that, or from those kind of more fabric-oriented harvesting elements like some of the recent attempts into this world. I think those we can think about as technologies. And I think that it becomes interesting to look at how materials that just basically, in some sense, capture air with different temperatures can become an extracting force. And I think the observations about energy, I think, are important. Like even like, for example, when you guys spoke about desalination versus osmosis and all of these other things. The problem with a lot of the large-scale infrastructural work, like I think there was some interesting examples. Also, one that was discussed in terms of how a dam becomes either an obstacle or it works with a kind of flow. And there's a strategic way of thinking about, you know, working with nature versus trying to resist nature, and the consequences of it are very clear. My general feeling, though, is that we should try to resist looking at that large-scale fixed infrastructure approach. I think that that is a kind of dominant way that people try to work with nature, with this like either a lock system or a dam, these kind of things, flood barriers. And I think in terms of the project, it seems to me, at least from my perspective, if I remove, let's say, the last couple of slides from how you guys were talking about the issues of erosion and, you know, some very profound large-scale issues, if I remove that kind of statement and I look at really the consequence of that impacting back on humanity in some sense, I think it would be interesting. Obviously, those challenges are really important, but I don't think the solutions to those challenges are large-scale infrastructure. I think maybe even some of these examples like you guys showed in Thailand and you know, the Aju people in terms of sea nomads and all of that, if we extract from those examples, not the social scenarios that forced people to live in some of these situations, but we just see the relationship to the environment in a way which is much more sympathetic and much more scaled to a more human-centric way of maintaining some of that social and cultural aspects, I think then we start to get somewhere pretty interesting, which, in my opinion, we can still deal with very large-scale issues, but not try to think of consolidated large-scale infrastructures as being the solution. And I think
this was a negative example, actually.
no,
Just in order to be able to evaluate how a smaller scale example works in a better way or in a more. Yeah.
No, I'm not mentioning it as a critique of that. I'm basically mentioning it in terms of where I see, you know, a process that can pose a kind of alternative model. Like those are very clear consequences of things not being addressed. But usually they're addressed in this way because the small scale solutions can't really deal with the large scale magnitude of those problems. So what happens is not a kind of negotiated space. What happens is a kind of very heavy handed, like the example that you showed of in Egypt with that large dam, which brings on a lot of conflict, right? Mostly because all of our water sourcing systems and so forth are definitely conditioned within territories, but you know the world doesn't operate based on kind of artificial delineations between countries and things like that. So I think the aspect of looking at it from a more ecological and symbiotic relationship to Earth, like you guys were speaking about early in the presentation, I think that's what we should try to hold on to. I think the problems of flooding, erosion, all of these kind of things, I think they are stated quite a lot. What I really like about some of the things that you guys are talking about is that solutions coming from a more human-centric place offer ways of developing strategies that could be more distributed and also set up a condition where this kind of more human and social aspects are one-to-one in connection with how those architectures are instrumentalized. So there was a couple of examples. The one-step well, which was very clearly creating all kinds of spaces that were both private and public, and really started to subdivide the space in a way that allowed for, you know, communal kind of activities to happen. I mean, those communal activities, you know, was everything from washing to eating to all kinds of different things. Somehow the architecture affords those things because it doesn't have an explicit kind of correlation between, let's say, shape, form, and let's say the activities that are going to be witnessed there. So I think I really like the material stuff. I think there are also some interesting ways of thinking about some of the suggestions that you guys have had in terms of some of the computational frameworks. I like the fact that you're, like, you know, just by default looking into Houdini, because I would suggest that Houdini is probably a good tool for this, and is probably a more useful entry to explore some of the stuff in a way that's much more, I don't want to call it friendly, but it's much more capable in some sense, because it's based on these kind of strategies than, let's say, N particles. So maybe the ways that you guys would use it would be different. Not to suggest that you have to be all in one platform, but I would, as you guys are exploring that space, I would really try to see what each tool can do differently. And there's a lot of softwares that are there that use particle-based ideas for fluid dynamics. We're not really trying to just do fluid dynamics, like just looking at water flow. So I think, for example, some of the ideas of just using kind of super cool water as a strategy, which, is basically liquid ice in some sense. It's like when it hits ice, that process immediately shifts from one to the other. And I think just the ways that we can somehow capture a little bit of the magic of this, I think is really important. I also like the fact that you broke it down into the way that we kind of talked about it: material, technology, and environment. And then the threat part, I think it's clear. I think the things that you guys put on the table, which is pretty outstanding, is the fact that, we have a certain volume of water on Earth, but very little of it is actually something that, let's say, we can use as drinking water. So when we speak about sustaining life, I think that there's something to be said about trying to find strategies that can extract and harvest on a local level. So that one example of that fabric, which I was trying to get the air team to really look at, but they didn't get very far with that. I think that's interesting. Those are technologies that we should start to look into. And as much as we start looking at some of these technologies, when you start to see that supposedly it's from 40 to 80 liters comparatively to the hard surface version of that, the French one that you guys showed, it's also quite outstanding in terms of energy, materiality, and, terms of thinking about variability of how we can think about stuff. So that's where I think that there's an interesting way of just looking at this in a way where we're not dominated by the large scale yet, but we use it as a driver to maybe help us take some decisions about how we may have the largest effect. So for example, like some of those things that people are doing a lot of land reclamation for example, like in all of the coastal aspects of beach developments, let's say, even very close to, let's say, Zaha's building in Florida is a good example. In Miami, like all of that stuff's going to be underwater. I mean, it's not if, it's when, and it doesn't stop those buildings from being built on the edge. And Miami is in the heart of, let's say, hurricane seasons and all of these things. So there are amazing forces impacting on this. But every year you have people basically throwing sand to kind of keep the beach there. And in England, it's even sometimes a little bit more funny, because it's not funny like in a comical way. It's funny in terms of like not accepting the fact that these land formations will change. They're being treated as something that is fixed because people have bought some expensive property on the edges of these things. And it's a very complex problem, but it's not one that we can win in that way. So I think, we can learn from some of these examples that you guys showed at the end of thinking about actually even what mobility means, or how does, not mobility in a mechanical sense. I would like the studio to try to harness energy in the least mechanical way possible. When we start to evaluate energy and we start to capture and to utilize this kind of matter-based idea of thinking about our studio, I think you can see a lot of latent energy in things. And I think the really interesting way is to think how that and how we can somehow develop a maybe much more social way of kind of thinking about how architecture couples these two things together. It may be a reminder of some of the more vernacular and historical ways that people had a more engaged relationship to their environment. So I mean, these are not necessarily solutions that have to be completely urban. I'm not suggesting that they aren't. I think we may find scenarios, but I think I would leave the openness of some of this in terms of where we apply the architecture to be focused really in terms of how we simulate, generate, and start to develop kind of more novel ways of thinking about some of these problems. So I think you guys are in a good place. I do think, you know, the ritual and the social to deal with the scarcity of resources and harnessing, harvesting, and, you know, creating energy, I think is more than enough to really keep us very, very busy. Some of the stuff like the touch designer things, I think it's good that somebody is starting to look into them. Not so much about making it into interactive stuff, but at this stage, it may become quite important later on in terms of human interfacing. But I think it's also about how we extract data. So you guys showed some data strategies. The metrics of evaluating and controlling things. I think, Daphne, you were speaking about the self-assembly stuff that self-assembly group at MIT is talking about. Their strategies are very passive. And if I'm honest with you, it's not an issue about if it should be active or passive. It's an issue of if there's agency or not. So for example, there's no difference between what they're doing and what's used basically to maintain shorelines, which is dropping aggregates. Depending on the nature of the aggregate, it can be more conducive to certain growth. So for example, there was a lot of people over the last 10, 15 years that were trying to use 3D printing to create coral reefs. Now, actually, you can make a synthetic reef that has nothing to do with the shape. It has to do with electrifying. You know, you can electrify with slow voltage some metal and you'll have corals growing on it and you'll have sedimentation being born from it. And so depending on where these projects are situated, I think there are very different ways that we would apply some of the technologies to it. But I'm always for trying to have a kind of, let's call it proactive relationship with the environment. Otherwise, the time frames that a lot of these things take, it's kind of like, you know, when Akim Menges shows this pliable wood that can open and close, and they say, look, Theo, you do kinetic stuff, and Akim is doing it in a very natural way. The difference is that that material, in terms of the laminates, I don't know if you've ever seen it, the model is very beautiful. And we've done these bending experiments with moisture in the DRL2, but the problem is that they're dependent on the size of the laminate, meaning the thickness of it. They're not scalable at all, meaning like you can't just take that and scale up and get the same curvature. And the time frame of all of those things may be 24 hours to see something just slowly curl. You see that with, you know, things in your home, or, you know, if you have some water leakage or something, wood swells. So in the end, it's not really a system that's controllable. So it has a very passive relationship, and all materials have a very passive relationship to things. So if the previous team kind of used the word self-healing, and I think that that's an interesting way to think about materials, like in your case, you know, I would really look at the kind of active strategies that are applied to phase changing, or, you know, these kind of ways of really situating beyond just like a a material that you would apply to the architecture and think about water as material. You know, I think this whole thing that you guys are showing in terms of materiality, I think is super interesting. But it also means that you also have to take a little bit of an abstract view of what that material is to be able to start to see some of those organizations. And that's where I think the snowflake generation is, I think, quite interesting, because in some sense, the snowflake generator strategy is really just an outcome of the environment, right? But the material itself embeds that in a pattern that is legible, in a scale that is very clear, and that's why we can have a taxonomy of snowflakes, and we can understand in principle how they're generated without necessarily having to be so explicit about what each shape morphology is. We understand it's a taxonomy, so we look for principles. And you guys also had some other interesting surface tension on spiderweb stuff and all of these things. You know, if you take stuff like that and you try to just model it, then it's something completely representational, right? If it's a technique that looks like something like this, it's a complete representation. But if you really see it from a behavioral point of view, it's not representational anymore. It's something that's prototypical and scale dependent. Some of those things you'll see are scalable and other things are not. So that's where you take decisions in terms of how you apply things. And that's why this is not just about technique. Does that make sense to you guys?
Yeah, it's yes, quite inspiring.
I mean, I think you guys have a lot of stuff there. I think the other thing that I may ask all of the teams, I like the fact that you guys are doing some of these diagrams, like slide 12, for example, or this slide. It's good because I start to see that information together, right? So even if you have, you know, we need to have some techniques that are basically organizing the material on our terms. I mean, you guys are going to have to put the book together at the end of term 2. We might as well, I think, already start to develop a strategy or a template for that book. So I may ask Gapo to send you a template, just so that we all have the same kind of template, B5, whatever page layout, just so that we can be doing that in parallel. And you guys can be starting to organize those, and we can use the book as a framework for some of these things like material, technology, environment. These are chapters that, in your case, that we can maybe start to see all of the work in some ways much closer together. But I think it's a good start. So thanks for that, guys.
Okay, thanks.
Thank you.
And Ola, I would ask you if you can expand on those diagrams to somehow bring some of those diagrams. I like the fact that you really showed also how many people are living within that. You know, it gave us, I think, a really nice way to cut across and see the different kind of impacts of those organizations and how many people it's serving. So I think that that's very important. Because we know scale is an issue, but also magnitude of influence is an issue. And one thing is the environmental, but the other thing is the kind of human condition of these organizations. So I think that that's really useful information too. So I like the fact that in all of the presentation, you guys are trying to make the information yours. So the diagramming techniques, I think, are important. And there are probably some other diagramming techniques that maybe you guys would want to look at. This is for all the teams. I'll put some links to people like Edward Tufte and things like that. There are these books on information graphics that are like the seminal informatics books that you guys can have a look at. So the guy's name is Tufte, Tufte. First name is Edward. I would have a look at his books because he references all kinds of diagrams, from a tube diagram to how people were, looking at mapping river flows and all of this other stuff. He shows a lot of different techniques. He's not an architect or any of these things. He's coming from information design. So there may be some strategies for some of that stuff that you guys can look at as a group and also overall as a studio. All right, guys, I'm mindful that we got 2 more teams to go, and it's probably not the easiest for my friends in China, so we'll move on to the next team.
We're the third team. Can I share the screen?
Can we do something instead of saying first team, second team, third team? Just let's be earth, water.
We're the third.
Because I think in some ways, I don't know. I like it to be a little bit less about first, second, and third, and more about the things you guys are doing. And at some point, you guys are going to also like come up with some fancy team names and all of that stuff. You're going to have project names, team names, everything's going to be branded. So I'm going to take the opportunity just to think about some of these subjects that you guys are researching. Okay, this is my air team. Let's do this.
Okay, so our current research is divided into 5 parts. The first part is the analysis of the concept of air. And in the part, we examine the meaning of air in different cultures. The second part is about the characteristics and the mechanisms of air in different disciplines. The third part is how to use air, involving the study of air structure and air materials. The fourth part is how to get energy from the air. And we believe that understanding and using clean energy should be the goal. And in the current situation, the highly efficient and the low-tech strategies can give us some inspirations. The last part, the last part is our focus on the issues related to life sustaining, which gives us a framework for discussion. And this is our methodological framework. We did some basic research first and then set goals in the context by modeling, judging, and running physical models to get the agency. And then as a result of new research, to set new goals. Firstly, the air in different cultures. Air is one of the 4 classical elements along with water, earth, and fire in ancient Greek philosophy and in Western alchemy. So in Japanese, Gaodai, and in China, air, which is also called qi, means life force and spiritual energy. It is one of the substances we deal with most frequently, and they take many forms. Things like gases, wind and clouds, and fogs, mirage, weather and climate, smells, breathing. Daniel, you can. Okay. No, it's in the air in chemistry.
Okay, Cedric Price said that I like air structures because it is the major structural element you can breathe and it smells of violet and you can't draw it. Next page, please. There are several kinds of air structures we have studied. Some of them may be not so intelligent, but we may inspired by several of them of how air was utilized. Next page, please. So here we collected some cases of air structures where air was used as a major material. In the first part, we want to talk about air spotted structures, air beam structures, air cell structures, and so on. And each of them has several interesting cases. Actually, we think the fifth one, the buoyant and lighter than air structures, may be the most interesting part because it harvests the solar energy to heat the internal air, which can keep the structure floating freely and gives many opportunities to transform. Next page, please. We can go through these cases quickly. The easiest air spotted structures are held aloft by low pressures pumped into the structure via air blower, but they need constant air to top up the internal pressure. Next page, please. This case shows the progress of how an air dome was inflated. Next page, please. And this air structure was also used in temporary structures. Next page, please. One of the most interesting cases was the Ghost Army decoy tank, which was used by the American Army to deceive the German Army during World War II. And the right one, atmosphere field, is an art experiment, shows that air and fabric are a very quick, lightweight, and inexpensive means to create structures and environment. Next page, please. Another structure was air beam structure. Large spanning enclosures can be created by this structure. Next page, please. These projects were created with one or a series of inflated members forming the struts, as they can lightening the overall frame and reduce energy consumption. Next page, please. Same here, this one was created as a mobile science laboratory, provides overnight shelters and storage facilities for rainforest scientists. Next page, please. An air cell structure is a double skin and low press structure which requires very little maintenance. Next page, please. This is a wider proposal to utilize the valuable rooftop spaces of many car parks in London. And the designer want to use air cell structures and air beam structures to create arts and sports venue. Next page, please. Then ETFE is a new lightweight material which is usually inflated by air to create a waterproof, UV transparent, and lightweight building skin. Next page, please. Or to use as an air cushion in varieties of environment. Next page, please. A structure floats in air can be achieved by reducing the density of air within the structure, which means we can use lighter than air gases such as hydrogen or helium or raise the air temperature in the structure. Next page, please. Like in this case, they use black plastic bag to absorb heat from the sun. Next page, please. Or this one capture the radiation of the sun through the transparent layer, while the black internal petals shorten the sun's wavelength, heating the air inside to create a buoyant structure. This is an environmental friendly way to achieve floating. Next page, please. Except that lightness is of development and low cost are also good reasons for why air structures are increasingly used as bridging systems, floating booms, and buoys. Next page, please. Such as in this LMCS system, which were used to deal with disaster relief situations. Next page, please. Air can also be used for movement, like pneumatic building skins, air structures, air muscles, and air springs. And in the pneumatic skin part, the artist also used solar energy to heat the internal air of each small fabric structure to form a breathable dynamic shading. When these small parts go together to form a functional skin, which we think can be a way of machine reacting to the environment. Next page, please. We can achieve heating and cooling through dynamic solar shading and breathable membranes. Next page, please. Just like this project, artists use solar energy to create a human skin-like device which can react to the temperature. Next page, please. We also got the air muscle structure to replace iron, which is much more safer. Next page, please. And air springs as buffer. Next page, please. In transportation field, air structure were also used to transport people through ocean or sky. Next page, please. In the right one, a number of air casters are combined to form a levitating plank with a support frame used here for lifting large aeronautical parts. Next page, please. Besides, air structures also being used to create fixtures and some materials with added air, like metal forms, which we think the feature of strong by light may be useful. Next page, please. For example, sheet metal was formed with high pressure inflation. The products are strong by light. Next page, please. The same as here. This shows the process. Next page, please. And here are inflatable lines which can come in a variety of shapes and sizes. And the right part shows pneumatic closures. The inflated elements give structure to the hoop of a skirt. Next page, please. Besides in metal field, reduction in thermal conductivity and a reduction in the die weight of material can also improve structural efficiency. Next page, please. A metal foam is a cellular structure consisting of a solid metal containing a large volume of a gas field. They are usually strong but very, very light. Next page, please.
Yeah, so then we move to the energy part. We think the air can directly be the kinetic energy or use the buoyancy. So it can also be converted to another energy like the electricity. Next page. Next page. This picture is the sailboat. So this is maybe the most common example to make the wind power directly as the kinetic energy. Next page. This page shows the car equipped with the sail can move forward like a sailboat. And now we have the advanced wind power vehicle. It can also run against the wind and have the good maneuverability just like the car. This vehicle employs a robot connected to the wheels and does not have a motor and battery. Next page. And we move to the buoyancy part. Next page. So this is the air balloon and it uses the hot air to fly. Next please. And this page shows a unique solution for the heavyweight transportation in some area that lacking the infrastructure. And this machine uses the buoyancy to fly. Next page. And this is a model car driven by the air pressure. It squeezes the controls to drive the gears and move the vehicle forward. And it is powered by the air pressure inside the bottle. Next page. And this is a helium balloon. We know that the helium is lighter than the air, so this balloon can fly. And this machine is very silent and very safe the energy. Next page.
Except to convert wind energy to kinetic energy, we can also turn it into gravitational potential energy. One of the most obvious utilization is cat, and from a view of history, cats also inspired many inventions. So firstly, cats are more than next page, please. So firstly, cats are more than 2,300 years old. Ancient Chinese people used them for military applications to measure distance and even for lifting men. So they knew at that early stage already they could carry large weights by the power of wind. Next page, please. In 1827, a fellow called George Pocock actually pioneered the use of cats for towing barges and races against the house carriages across the English countryside. Next page, please. Then, at the dawn of aviation, all of the great inventors at that time, like Hargreaves, like Charles Lamson, even Alexander Graham Bell, the inventor of the telephone, was flying this cat. Next page, please. Well, those are all about what we did in the pursuit of aviation. Next page, please. Then the Wright brothers came along, and they were mailing flying cats to develop a control system. The first ever 20 seconds human flight was fantastic for the future of commercial aviation. Next page, please. That was until the 1970s, where we had the last enemy crisis. A fabulous man called Miles Lloyd wrote this seminal paper, which was completely ignored at that time. It was about how to use an airplane on a piece of string to generate enormous amounts of electricity. The real key observation he made is that a free-flying wing can sweep through more sky and generate more power in a unit of time than a fixed-wing turbine. Next page, please. As we all know, current wind power generation relies on rigid supporting structures and is limited to altitude up to 200 meters. But wind at higher altitude is significantly strong and more persistent. To access this major potential of a renewable energy, kite power generation may be a solution, because it may harvest the winds high above the earth and generate electricity at a low cost than wind turbines. Next page, please. There are mainly three kinds of kite power generations currently. The first kind is small turbines that are suspended in the air with a large helium balloon, but they only produce very little power and are not easily scaled to a large size. Next page, please. The second system just looks like two cats that are tethered to one spool. They are powered an electric generator, but also feeds a hydraulic accumulator, which stores potential energy in the form of a pressure that can be released to smooth the cat speed to an essential quality and makes the system's energy output compliant with the grid's needs. This system can be deployed in less than 1 day, potentially being used for disaster relief situations where energy has been cut off. Next page, please. This third one is a container wind power system developed by a Swiss company. When there is wind on the ground, the plane spin to lift itself into the air, and the plane can convert wind energy into electricity. Next page, please. So we think cat power may be the world's magic solution to the energy crisis. Next page, please.
So about the environment problems, we already have some international conferences pointing out the serious environment issues. And nowadays we have several problems about the environment related to air, like the haze, the greenhouse effect, the hurricane, and the spread of virus and ozone hole. So we should take this into our consideration to solve these problems. Okay, that's all.
Hey guys. So, I mean, I think you guys, sorry, can you hear me?
Yeah.
Okay. I mean, I think there's a lot of aspects of what you guys have talked about which are interesting. You guys have taken an approach of like really seeing all the different ways that people have utilized air, from air structures to air as energy, mobility systems. So, I mean, energy is a big part of how you guys have been looking at it. And the other part, I think, is really about structures that deal with force. So, one of the things that you guys have kind of put on the table, but I think it sometimes is not so evident. Like, for example, when I talk with David Green, I mean, air is mass, right? So air is this kind of thing that's all around us. And for example, an inflatable, and some of the references that you guys have shown, I think are pretty amazing, because the ways that people have been dealing with somehow using air as pressure is either through really micro thin membranes, like you guys have shown, or for example, like in the kite strategies, I think what's interesting is that the geometries of this now start to become very different than what we would assume would fly, right? When you look at Alexander Graham Bell's structures, or at least the first time that I saw those kites, those box kites and those pyramidal kites and things like that, like slide 71, for example, I really didn't understand how they flew. And if I'm honest, until I build one, I don't think that I will really understand. Because somehow they somehow defy, how can I say this? They don't look like they should fly. Like, I can understand Buckminster Fuller's concept of making that large floating city much, much easier, you know. It's just because it's very easy to kind of understand a certain amount of hot air rises. So if you trap that, you can lift it. So for example, the difference between, you know, some of these air balloons that are using just heat, or like a candle, you see that rising and you can understand that relationship pretty clear. When I start to look at the Alexander Graham Bell relationship, I start to not understand how it works. Now I'm talking about me. You guys are probably much smarter than me, so you understand all of this stuff, I'm sure. But I'm just saying it from the place where the appearance of things also offers a way to create, I think, some very strong presence. Like some of the examples that you've shown, and even the paper that you brought up about kite power, which makes sense as soon as you said it. That of course, like if you're trying to capture air, the difference between having something passive that's stuck and fixed, that needs to spin in a certain way with already a bias, where something that is super responsive, it made total sense in some ways that there should be ways of being able to harness that. So I think that there are a lot of technological things that you guys have explored that I think is really interesting. Another thing though that made sense to me was in the beginning you guys were talking about air, and the one thing that I thought about was a kind of more human thing, that air and the sense of smell is very connected, meaning like air really is a carrier of particles. It's a way of thinking about a lot of things. So you guys have shown a lot of architectural and mobile machines, and I'm just curious of other things that are designed to basically use air. For example, seed dispersal of plants uses air. I'm thinking about things like, perfume or any of these other things. There's very strange things that we don't realize because atmosphere and air is invisible in some sense. So there is something to the project about making the invisible visible that I think is important. But I think that also means something different if we look at the different senses that we are exploring. And the reason I'm bringing this up is because I think it could have an influence in the ways that you kind of maybe do some of your experiments. And I also think that what I like about the project is that there's such a richness of already existing kinds of ways of approaching things, from some which are active to some which are totally passive, that I think it already sets up a kind of systemic approach. What's not so clear, and I think is something that you guys have to start to consider a little bit, is how would we work to simulate some of these things? What are we actually simulating? So for example, when you guys use the word breathe, I think you said breath or something like this at some moment, somebody mentioned this, or maybe it was just my imagination. But I keep thinking about the difference between some of these membranes which are completely enclosed and other membranes which are breathable, for example, that are designed to let flow of air come in and out for different reasons. Like when we're talking about survival, which is something that you didn't talk so much about, but I think you guys should think about it a bit, is, of course, energy is very important because we can use it in different ways. But I also think this ability to think about cooling, or thinking about how air is a way that really shapes our human conditioning. So for example, a very mechanical way is like air conditioning, right? We have a machine that's changing temperature. But you realize, your sneakers, for example, are designed to also dissipate air, for example, right? They're breathable, so that when you're running, the heat that you're generating is coming out of your body, so the moisture that is coming out. And I think we should think about maybe some of those technologies, about what makes, things that like textiles that make it breathable, things that allows ways of thinking about the environment based on temperature. So because air is a carrier of a lot of different things that affects us as a human, I think you guys have focused on some of the more structural, spatially defined ones. The Graham-Stevens examples, I think, are very interesting, like the one that you did in Kuwait, because you start to see how that can also extract moisture. In the middle of the desert, how you can create basically, an extraction of water, which is different from, let's say, the previous team's mesh, for example, which is really like a rain catcher. The surface of Graham-Stevens thing is really trying to design the difference between transparent and dark material, and trying to really capture it from this perspective. Same material, different coating. And you can have examples like some of the things that Thomas Saraceno has tried to do, and some other people. But I think we should look at this aspect of air as material in two ways. One is from air structuring space and structuring physical structure. But I think from the other side, air as a survival, either as an extractor of things that we need, like water, or air as a way of heightening senses and environment. So those articles that I gave you about Rainer Banham and the kind of idea of a well-tempered environment. I think these are important for you guys to maybe think about a little bit. So I think the aspect of also, I remember now when I thought about breathing, when you guys made the relationship to buying air, people trying to sell air. You know, another strange thing that happened in London at one moment in time, there, because I moved here almost 20 years ago, there were oxygen bars, places where you would go just to have different kind of air. So people were trying to sell you different kind of experience attached to air. And sometimes, you know, for me it was also very weird because I don't think so much about this. But the fact that this was something tied to experience, different kinds of place, the way that they were thinking about things was also something that in a strange way, like an inflatable, separated a certain volume of air from atmosphere, right? So one of the examples that you guys showed was Ramblar in Berlin. So I've been in one of those bubbles. So it's like at the back of a truck, they make this inflatable and all of these other things. And strangely, it's quite comfortable. You don't feel anything. It's one airlock at the end. And very easy. I had a dinner in one of these things after an exhibition in Germany. And but the size and the scale of it matters. So for example, at that scale, it was okay. I made some inflatables with some of my students in Germany one year, and there wasn't a problem of breathing, but the material that we were using, which was cheap plastic, had a very strong smell. So for example, you don't smell it when you open the plastic, but when you enclose it and the air can't move, it became very pronounced. So that's why I was thinking a little bit about some of these other aspects, because air has a very strong sensitivity for us to create the conditions for us to feel comfortable or for us to really behave in a very different way. So even slightly different elevation of air or pressure makes our behavior change very differently. So it's not just about breathing, it also affects other aspects of humans. So it's interesting to think about a position that you guys will think about in terms of your architecture. Is it trying to resist the environment or is it trying to harness the environment? You guys have presented both options, and there's probably not an either or perspective, but these bubbles that we see right now, these bubbles are really separating and creating space with the most minimal, and they're using air to structure space, right? It's very different than the air beam. For example, in the States, in Detroit, I remember I went and I saw the old football stadium, which was the largest pressurized air dome. And at one point in time, all of that is just about the internal pressure inside. The dome itself was not crazy structure, but it was about a controlled pressure inside of the stadium that at that scale could allow it to basically really create amazingly large spaces. And I think like there's that aspect of lightness and all of these other things, which I think is really important. The one thing that I would ask you to look at though is I would look at air with respect to farming, because I think aeroponics is actually a quite interesting science for generating food production. Do you guys know about this? Have you looked at it at all?
Yes. Maybe different chemistry composition will help the farming to become faster or slower.
Yeah, I think the only thing I'm suggesting is like, I think it would be useful for you guys to introduce that element in some way. How can we think about growth in some way? I'm not talking literally about making farming, But I think at some moment, inadvertently with our architecture, because we should think about how people are going to use this in a way. Water is a good example. That's very important and precious. But I also think the way that people can cultivate food is very important. So the examples you guys are showing right now, like for example, what I see right now on the screen, these pavilions, there's a very specific relationship between the architecture inside and outside. So for example, nature doesn't come in. It's like a hermetically sealed thing. And I think when you do that, you either have to create a new nature inside. That's why they did a lot of these biodomes and stuff like this. If you look at a man named John Allen, he did something called the Biosphere, or the Biosphere 2. I think they just did a movie about this. I think you guys can watch it. Because I think the aspects of the social become important to talk about. So for example, if you look at Biosphere 2, it was people that were trying to be separated from the world. Like if the world, it was a living experiment for a year, people living in a dome together. So maybe you can watch and see some of these issues that happen. So I'm just speaking about it so that you have maybe more ways of thinking about inside, outside, about breathability, because I think the examples of what you guys are showing, I think is very powerful as technologies. So some of them I didn't know, for example, and which I think is also nice when I learn new things. So this is positive as well. But I also want you guys to think about the social aspect of air and the food production aspect that you guys can look at. So I think your approach is really looking at these things from a technological place, and I think we can look at it in a human way, just like we were talking about the sense of smell, and just how we were talking about air as almost like an infrastructure. I think you can consider it as a volume which doesn't have a clear delineation from inside and outside. Does this make sense, or am I confusing you guys?
Yes. Can I discuss some question?
Yeah. Can I ask one thing? Can you want to just turn on the light so it doesn't look like I'm
very dark?
Total darkness. Just give me 1 second. If I can even see it. Yeah. Okay.
Can you turn to 34?
Oh.
Sorry. Okay.
Okay. Which page?
34.
This?
34.
Yeah.
This one is create a space both for only one like structure, but both like interior and the outside space. This is like for the more open to the public.
Yes. Yeah, I'm just thinking, like, if you think about, for example, a sneaker and how people are designing sneakers these days with knit technology and stuff like this, they want air to pass through. So your foot, for example, doesn't sweat, or so you don't get too hot. It's an issue about comfort. And in different technologies, people are using it. So I don't think it's an issue so much about being able to be both inside and outside. It's more about potentially how we think about these surfaces and how we think about pressure and how we try to capture or harvest energy. It's these things that I think with each of the examples, it could mean something totally different. What I like about your projects, your references, and the way that you present it, it's quite focused on what it's doing. The things that you guys are showing, like kites are a study in its own, right? Lots of references, either really about generating an energy system or about, augmenting something like a vehicle. There are a lot of different ways that it's being used, and I think that that's a really good resource, and I think you guys should catalog them in some way. But what I'm suggesting is that you expand a little bit the research to introduce some other variables as well. That's why I'm saying the thing about potentially looking at aeroponics or other ways of thinking about air, and maybe more aspects that have to do with food or production of things that sustain life, to kind of open a little bit more territories, if that makes sense to you guys.
Makes sense.
Yes.
Sorry, Gajah, you want to say something? You wanted to ask?
Yes. Actually, we want to make some simulation in Maya or model something, but we find it's very hard to kick off because we don't know what the problem should be solved. So do we need to set a background or focus on some social problem like the industrial haze or to save the forest fires?
I don't think that you need to have a program. I think the challenge that you guys will all have in different ways is the fact that the reality of things is that you're not modeling something, right? At this beginning.
Yes.
So it's not really an issue of geometry. It's an issue of trying to extract behaviors and principles of air. So, for example, a lot of the things that you guys have shown are pressurized systems, right? The thing that maintains the pressure is the tailored piece of plastic or the tailored piece of fabric, right? That's what's kind of constraining and creating the pressure. So for example, when you guys show the air muscle for why we can change from a piston into a pressurized air system, if you look at something like Festo, do you guys know Festo?
No.
F-E-S-T-O. You can look at things like their air muscles. You can do it here so we can look at it together. Festo. S-T-O. No, you did it right. T-O. Space. Just hit space bar. No, sorry. Just create a space, yeah. And just put in bionics. B-I-O. Yeah, there you go. And just go to images, for example. So, I mean, these guys use a lot of air pressure to actuate things. And you'll find some flying systems, all kinds of things. Go to videos, maybe we can see that easier. Sorry, I can't reach any.
The third one, the video. Yeah.
I mean, they develop a series of technologies. But one of the things that they do is soft muscles. So for example, soft muscles is just using air pressure. Now, some of these are not always pressurized systems. They're different things that they've been building. They do a lot of biomimetic stuff. But they have a whole series of flying systems and a whole series of gripping systems. It's interesting because I haven't seen this robot, but they've talked. Anyway, they're people that I've talked to quite a lot because they were interested in some of the mobile voxels. But you see that a lot of these systems are soft, and a lot of it is using air pressure to make something that can naturally grip. Or for example, they use these soft gripper systems that uses water. So pressurizing water, pressurizing air, I think is also very different. You'll start to see some of these butterfly systems and some of these other things. I think that there are different ways of working on some of these challenges. But if you look at soft muscles, you'll see like airborne strategies of thinking about how to design using pressure and tailoring things. Because in some sense, you could simulate by using a relationship between patterning textiles and inflating them. That's what I was trying to do with a lot of the students last year. But I think air is something different when it's pressured within an envelope or within a sock or whatever these things are. And it means something totally different when it's released in an atmosphere. And I think your project is going to have to somehow balance between these two worlds. Does that make sense to you?
Yes.
And I think Festo has some very beautiful examples that I think could be also very contemporary ways for you guys to look at some of the technologies. What they tried to do, which I think is very important, I mean, they're an actuation company, but what they really tried to do is make the piece as light as possible. One of the things that's kind of funny is that they really believe in biomimetics, but obviously this isn't a bird, and it's not looking like, it looks like a bird, but it doesn't really behave like a bird yet. But these models, if you look at the first ones to this, I mean, this looks a lot more bird-like than the first attempts, which were more gliders. And you'll start to see the development of how they're starting to use materials, because in the past, they were more like a piston company, more mechanical. Now these elements are becoming lighter, lighter, and lighter, and they want to be able to control them. So they start to develop a very different way of thinking about how to design. And yeah, I find them very interesting company. So for example, air is also used in a negative way. So if in a positive pressure, you are creating something that expands, in a negative pressure, you can create something that's gripping, right? So if you suction air out, you create a very, they're used for grippers on robots and things like that. So I would just look at this idea of pressure as both positive and negative. I would look at the difference between capturing things that can be pressurized versus looking at things like an atmosphere, because I think that has also two very different ways of thinking about how I would approach simulation. For those that really want to have explicit modeling, patterning things as an explicit thing, but then letting it be inflated, either is going to be like an inflated tank, like that reference that you guys showed, which I didn't know about, but it doesn't surprise me. Or inflation based on elasticity of what that material is would have deformation, right? So if you see how a frog breathes and you see the neck kind of expand and contract there's many different kind of vascular ways of thinking about breathability. So I would just ask you to kind of conceptualize some of that and try to add some of these other strands of research to what you're doing, because I think it'll be very interesting. Does that make sense, or do you have other questions?
Yes. Last question. Do you remember the name of the movie you just mentioned?
Do I remember the name of the movie that I just...
Yeah, you just mentioned a movie about the air.
Did I? I have to say, Gauja, I don't know. I'm very tired, so if I'm mentioning things, it's recorded and you can have... I mentioned a movie about air. Since all your classmates are listening and my mind is not maybe so fresh, and maybe they can tell you what movie I mentioned.
Okay.
No, I'm asking. Did I mention a movie? I wasn't sure.
I didn't hear that.
maybe I'm wrong.
Ajay, you're just trying to confuse me and express very honestly that I'm very tired. I understand. I'm starting to learn about you. This is a joke. Just like, haha, joke, funny. Okay. If I recollect anything, I will send it to you guys, okay? I think right now, just think about this breathability stuff. Think about the difference between simulating atmospheres versus inflation and pressurized systems that have a geometrical delineation of space, okay? Look at Festo, because I think Festo has a lot of interesting examples. Look at soft muscle systems, which is something that is using air pressure to actually, like a structural beam, have a lot of energy that's encapsulated. The same ways that you guys were showing the kind of inflated aluminum and all of these other kinds of research. I think you have a lot of looking at inflation as a way of utilizing air. Now just take it from a more survival place. So I think you guys are working more in terms of interesting architectural ways of thinking about materiality and using energy to create space. Now think about it in parallel to ways of creating more survival-based kind of strategies for the human. And then I think we'll keep working on it. Okay. But I think it's a good presentation, and I liked the examples. I also think you guys are taking the project in a different way by having so many kind of prototypical ways of working with air, which I think is useful too. Okay.
Thank you.
There is a method to what we're doing. I know it seems like everything is free, but these presentations are all very interesting, aren't they? What your classmates are doing. So I think we're slowly starting to really construct a way of understanding the world. We have one more team.
Yeah, I will show my screen.
Yes. This is the fire team, right?
Yeah.
Okay, cool.
Yeah. So, welcome to the discovery of fire. And the team members of our team is Penny, Yunpeng, and me. So, I catalog these things for 5 parts. And the first one, we talk about the combustion. And next, we will talk about the fire for life and manufacture and architecture and environment. So the first one is the combustion. Actually, when we mentioned fire, most time we talk about the process of combustion. So at first, we started combustion from the following aspects, like reactant, products, and stages of fire, spread, and how put out the fire. So I think the first one is the stages of combustion. And I think it's easily to see the relationships between the heat, fuel, and oxygen. You can see the energy exchange between the reactant and something like the products of combustion. And it's stages of combustion to talk about the ignition and how growth and how decay. And next is about the basic properties of temperature. And this is a example to show the temperature of a body. It's a curves 16 screen photography for a long time. In order to achieve it, use it on military infrared cameras from 30.3 kilometers distance to detect body heat. And And the technology for remote border enforcement and tracking and search and rescue constitute the European Union response to mass immigration, part of a complex military humanitarian crisis. And it allows viewers through the body temperature, a fragile body, temporary national racism, and biological energy, the politics of dice, and rethinking the situation of refugees. And this one we talk about the material that prevents heat from escaping. And the lying fabric adopts OMI 3D thermal reflection technology. And the iconic human-shaped OMI thermal reflection pattern can effectively improve the thermal reflection performance so that every part of the body heat is firmly locked. And this one is the products of combustion. I think it will be the most important of the combustion part. And the energy of the flame can change the form of the fuel and the molecular form. And there may be different chemical reactions for different fuels, and at the same time show a different flame path and particle effects. And next part, I will talk about the fire for life. And I think it's related to the human how use the fire, and it's from the next part, like friction and warmth and light, hunting, disinfect, cooking, and human. And the first thing is about how to produce fire. It's a device for making fire and the principle of heat generation by friction. And also the convex lens also had the function of concentrating light. After the sunlight is refracted through the convex lens, it will converge at the focal point. The energy of the light at the focal point is a lot. And if the flammable articles are placed at the focal point, it is easy to ignite. In some cases, we can even make convex lenses by using ice to focus the light. And the heating system is also a general way for people to get warm in winter. So there are two kinds of traditional way. We all use the smoke from the combustion and make a tube like a chimney to pass the smoke or the hot air from combustion to hold the temperatures. It's a traditional Chinese way and a traditional Western way. And next we talk about the electricity. And energy can be converted on some devices, and the first process is cold combustion in the boiler produces a lot of heat. It is chemical energy changed into heat energy. And the second is about high pressure steam through the steam turbine and the heat energy into rotary power. And this is the heat energy changed into mechanical energy. And finally, we can make fire, the heat change into the electricity. So as for the electricity, we can think about the light and the solar energy and the relationships between them. So the ability of some materials can create an electrical charge from light exposure. Like photovoltaic modules use light energy from the sun to generate electricity through the photovoltaic effect. And the photovoltaic effect is the generation of voltage and electric current in a material upon exposure to light. It's a physical and chemical phenomenon, and they all can be used in the solar hybrid power systems. And it's the solar hybrid power systems are hybrid power systems that combine solar power from a photovoltaic system with another power generating energy source. And the solar vehicle is an electric vehicle powered completely or significantly by direct solar energy. And it can be the solar cars and ships or the space things. And next is the light from the combustion. And we talk about the phototaxis. It's a kind of taxis or locomotory movement that occurs when a whole organism moves towards or away from a stimulus of light. And this gift is a kind of lever, positively phototactic. And that is mediated by simple icebergs that consists of a pigment cell and a photoreceptor cell. The photoreceptor cell synapses directly onto ciliated cells, which are used for swimming. The icebergs do not give spatial resolution. Therefore, the larvae are rotating to scan their environment for the direction where the light is coming from. And photokinesis is a change in the velocity of movement of an organism as a result of changes in light intensity. And also the plant also have the phototaxis because of the effects of move length. And both the animals and the plants can be influenced by the magnetic fields. And fire can be the temperature. So we find the flaming can produce high temperatures, and the high temperature can disinfect. And this part is about the human from the fire. And sorry, I think it's a little mistake. And the process of using fire, the primitive man become more and more dependent on fire as he lost his hair, especially in winter when people left the fire to go out or look for food. They felt very cold and had to start thinking about ways to keep out the cold. In ancient times, the ability of human beings to resist natural disasters was very low. They may have started eating cooked food when they were so hungry after a fire that they had to look for food in the ashes. But when they found cooked food to be more delicious than raw food, they took a big evolutionary leap forward. So next we're talking about the cooking. And ovens are often used for cooking, and where they can be used to heat food or to a desired temperature. A microwave oven heats food by passing microwave radiation through it. Many molecules are electric dipoles, meaning that they have a partial positive charge at one end and a partial negative charge at the other, and therefore rotate as they try to align themselves with the alternating electric field of the microwaves. Rotating molecules hit other molecules and put them into motion, thus dispersing energy. This energy dispersed as molecular rotations, vibrations, and translations in solids and liquids, raises the temperature of the food, in a process similar to heat transfer by contact with a hotter body. And this video is about the realization of the radiation, and it show how the microwave oven worked. And next we talk about the hot air balloon. And the process of combustion can produce hot air, and the hot air balloon uses the hot air from the combustion to control balloon combining or descending, and it also uses the buoyancy of the fluids, and I think it can be related to the air and water. And the next part we talk about the manufacture. So it can be from these parts like aerotechnology, carting and heat transfer, and thermodynamics. The first is the fireworks. Fireworks is a more complex way to use fire, and the ingredients of the fireworks is really simple, only produced by 3 ingredients. But how to control the height, size, shape, and color is more important for fireworks. How to control the height is more like a small rocket. It needs a lift charge, and a larger firework not only requires a larger lift charge, but a larger explosive charge to propel the insides outward. A burst charge is a pyrotechnic mixture placed in a shell, which is ignited when the shell reaches the desired height in order to create an explosion and spread the stars. As for color, it was decided by the presence of certain elements, primarily metal ions, based on each element's characteristic emission spectrum. And this is artwork from the artist. The artwork named Skylander. And the lander is 500 meters long and 5.5 meters wide, laid on the ground and lifted vertically into the air with a hot air balloon. It has a difficulty to capture for a certain period of time to meet the visual requirements of the work. And the next is the heat treating. Heat treating is a group of industrial, thermal, and mental working processes used to alter the physical and sometimes chemical properties of a material. The most common application is metallurgical, and metallic materials consist of a macrostructure of small crystals called grains or crystallis. The nature of the grains is one of the most effective factors that can determine the overall mechanical behavior of the mantle. Heat treatment provides an efficient way to manipulate the properties of the mantle by controlling the rate of diffusion and the rate of cooling within the macrostructure. Steel that has been freshly ground or polished will form oxide layers when heated at a very specific temperature, and the iron oxide will form a layer with a very specific thickness, causing thin film interference. This causes colors to appear on the surface of the steel. As the temperature is increased, the iron oxide layer grows in thickness and changing the color. And this video is show the deformation of the mantle and what the structure of the mantle will be. And flame cutting is a thermal cutting process that uses oxygen and the fuel source to create a flame with enough energy to melt and servo material. And the use of oxygen and fuel in the flame cutting process is why it is also often referred to as oxy-fuel cutting. And flame cutting uses a natural flame to heat the material up to its kindling temperature. And the pattern is about the examination of flame cut edges is the surface of the cutting edge. And robots can automate the process, which is unsuitable for humans because it dissipates a lot of heat, either from flame or from electricity. This is the control of fire that we humans have when we are dealing with manufacturing. And the CNC cutting machine is to use digital program to drive the movement of the machine tool. And equipped with flame cutting system, the use of CNC system to control the switch of the flame cutting system, the steel plate and other metal materials for cutting. And the next is the military flamethrower. It was used in World War, and the flamethrower consists of a backpack and flames and a flamethrower. Backpacks typically have 2 or 3 cylinders, one containing a high-pressure inert propulsion gas, such as nitrogen, and the other 2 containing a flammable liquid, usually a mixture of gasoline and some thickening agent. And this is about the far infrared flame. A sensor can detect the infrared light with wavelength within the and the far infrared flame probe transforms the intensity change of the infrared light into the change of the current. And the stronger the infrared light is, the smaller the value is. And the weaker the infrared light, the greater the value. And this is about the radiation. The heat transfer coefficient of the radiator mainly depends on the heat transfer coefficient of the air side outside the radiator surface. And in the case of natural convection, the heat transfer coefficient is mainly related to the heat transfer temperature differences. So this is we try to control the heat emissions with machines. And this is the principle of thermodynamics. The law of thermodynamics is the most philosopher significant. This would explain the ordered structure of living things on Earth. Life on Earth is an open system that maintains itself in a low entropy ordered state by ingesting low entropy substances from the environment and releasing high entropy substances into the environment. And from the thermodynamics and entropy, we can study the system models to find how the molecules work and how it relates to the living cells and what the life is. And the chemical composition, mineral composition, and the macrostructure of refractories determine their properties. And the chemical composition of refractory materials is generally divided into make component, impurity component, and additive component. The first picture is about the structure of the refractory material, and the second is about refractories are destroyed by thermal shock and structural damage. And next is about the fire in architecture.
So architecture should not just build the spaces, but rather create temperatures and atmospheres. Here, 2 horizon metal planes are extended at different heights, like a miniature Gulf Stream. Their position creates a movement of air using the natural phenomenon of convection, in which rising hot air cools on contact with the upper cool plane, and falling, it's then reheated on contact with the hot plane. This is creating a constant thermal flow. Next. The first temporality taken in the envelope of clear glass is in real time the time of natural solar course. The second temporality is built with the yellow-colored glass envelope, blocking the wavelength of the light responsible for the fall of the melatonin in the body. The third temporality is defined by the envelope of the blue glass, of which wavelength block the secretion of the melatonin in the body. Okay, next. This part is about the heat in the architecture. Next. This project was created by the Norman Foster. So Apple Park could not be ignored. After all, it is an advanced technology company that can do without air conditioning, even on the hottest days. Not only can the solar panels provide energy, but the ventilation inside, including the details of design, is also involved in temperature regulation. To this end, this is a breathing building that serves as the breathing regulator for the entire room. Next. Flamboyant was an ornate style of late Gothic architecture that began to flourish in France around 1350, and was eventually replaced by Renaissance architecture in the early 16th century. Okay, next. The fire part is about fire for environment. So in order to sustain a sustainable fire management, the first one is avoiding or minimizing harm to the environment, including the quality of the air, land, water, and the biodiversity. The second is about maintaining or improving the biodiversity. The third is about using regime management to reduce the occurrence and the intensity of bushfire across the landscape. The fourth is about meeting legal and policy obligations for environmental care. Okay, next. So this is about fire management. These are some methods of fire management. The first is satellite technology. Second, fuel analysis, wind analysis, high-tech fire shelters, and so on. Okay, next. So after the forest fire, the trees grow more exuberantly. If the fire is properly used, the benefits are mainly as follows. Clean up the dead branches and the dead trees. At the same time, soil temperature increase the decomposition of the organic matter, releases nutrient elements and minerals, increase its usability, improves soil fertility, and promotes material circulation. And the second way is eliminate old dead tree species, reduce the spread of germs and insect pests, and provide opportunities for the growth of new tree species. And third one is reduce forest leaf area, reduce canopy transpiration and water retention, increase soil moisture content, and protect water sources. Okay, next. Plant ash is the ash of the burning plants, so it contains mineral elements in plants which promote the reproduction and the growth of the flowers plants. So the products of the forest fire burning are not necessarily harmful to an extent. They are also positive. Okay, next. So Flaming Mountain is the hottest place in China with the summer temperatures as high as 47.8 degrees Celsius. Surface temperature as high as 89 degrees Celsius. And could cook eggs in the sand nests. And you can see the effect of temperature or flame on the building and the environment, on the style and the materials of the building. and the unique temperature corresponds to the unique features of the landscape and the different styles of the building. Okay, that's it.
Okay, guys, thanks for that. I mean, I think that there are some aspects of what you guys presented which I think are pretty interesting. When you guys started with, I mean, I could somehow organize this stuff in a couple of different ways. One is literally fire as material that you guys are talking about, fire as process. And then I think you interpret fire as heat and fire as light, right? These are the basic kind of thematics that are being addressed. The technologies that are associated to some of these things, I think, are also kind of interesting. So, for example, you guys showed Richard the most use of thermal cameras. Or, for example, when you guys were talking about the work of Philip Rum and things like that, he is also obviously also interested in atmospheres. But, for example, I think Philip Rum is a good example of somebody who can speak to a lot of the things, has an interesting diagrammatic process. Like his drawings are very beautiful, his diagrams are very interesting. But when he translates that into architecture, or what he calls architecture, there are some problems. So he tried to do something in Taiwan in terms of a park, and his idea of constructing these kind of architectures are very different if they were in an interior situation or an exterior. What I quite like about some of the things when you guys start to abstract literal fire into heat and light is certain kind of implications about how that somehow has a very immediate relationship with living systems. So, for example, when you guys were talking about phototaxis and photokinesis, maybe one of the most beautiful examples of photokinesis is, for example, if you've ever been to see sunflowers in a field. The sunflower, in some sense, is designed basically to continuously rotate to capture as much sun as possible. Because of its phylotactical relationship to a lot of seeds, it has very small petals. So the way that it adjusts that, it has a very complex stem that allows the flower itself to rotate. And I think that becomes really interesting when we think about the individual flower and what that means in the collective field, because you start to see this kind of rotation systems. I had some examples that I could show if you guys want me to share my screen for a second of some other aspects that you guys spoke to, which I think are interesting. And I think they're interesting in different ways. I think they speak to, like when you guys talked about the sky ladder and the fireworks and color and light and heat. These are all the kind of attributes that one is talking about when it comes to some of these things, right? One second, let me see if I can share my screen. Okay, my screen is a disaster, so. And also for Gauja, it's called Spaceship Earth. I did mention Biosphere too, so my apologies. My memory happened a bit later. But for you guys right now, I don't know if you know this artist named Dan Rosengart, but he did a recent project for farming, and he's using, I don't know if I should play this now, but I think you guys can have a look at it. But he's trying to make a correlation between light and food production and the difference between synthetic light and obviously plant growth that's basically using, obviously, natural light to grow. So he's trying to extend the hours of those kind of things by introducing a way to create artificial light to continue growth processes. And what I think is kind of interesting for this is he takes something like a farming field and he turns it from a piece of agriculture into a lighting field. So it takes something that is natural and takes something like an artificial light, but the light is not there just to amplify, it's to help continue the growth of the plants. So the same ways that people use kind of artificial lights to keep gardens growing, he's trying to do a similar way. Now, the reason this kind of comes up is like when you guys are talking about photokinesis and phototaxis and all of these properties, these are features that is obviously really responding to the sun. Here, this is a kind of strange project because in some ways he's trying to augment that relationship by deploying kind of artificial light. So if you look at these things, he's using different kinds of ways of somehow playing with lasers and different kinds of ways of lighting it to create a kind of different field space. He's using it more as a way to communicate. So in the same way that you guys are presenting the fireworks as a kind of display, here he's creating a kind of artificial ecosystem that he's trying to somehow bring attention to farming, but he's also using light as a kind of strategy to illuminate. So you can have a little look at that kind of stuff. The other one, when I think about fireworks, like you showed the sky ladder, and I think that that's a quite beautiful project. But one of the issues around fireworks and fire and all of these kind of event-based strategies was maybe discussed by an architect like Bernard Tschumi in the most convincing way. So he's famous for doing this project, which is the Parc de la Valette. I don't know if you guys know that. Do you guys know that project?
Yes. We went to the site.
You went to the site, yeah. So it's all these red follies, these kind of drawings that became quite famous. But actually for Tschumi, the reality of the project, or what he was talking about in terms of events, was much more understood from his fireworks display. So he designed the fireworks for the opening of Parc de la Valette. Tschumi is quite famous for basically speaking about event in architecture. And he basically said in a very strong way that actually the fireworks and these drawings that he did to really speak to that in terms of drawing what the fireworks strategy would be was actually the true event in architecture. So the follies, of course, spoke to a certain kind of way of thinking about what he was calling disjunction, but the fireworks is really what fostered this whole real model that he was talking about in terms of event. And the reason that I'm stating that is that when I did my presentation, for example, I showed stuff like the Peter Zumthor using fire as a way to subtract material, right? And you guys talked about the different kinds of features of ash and charring and all of these things. And those things I think are very important. So your examples of the forest, for example, is very important because that cycle of life of nutrients and the whole notion of burning off, I think, is very important in terms of thinking about the kind of ecosystem. So fire in a generic sense is usually thought about as something destructive. But in that opportunity that you guys showed with the forest, if it's done in a controlled way, you are basically generating new life for the forest, right? You're regenerating nutrients. You're basically helping that. So the relationship between growth and fire directly has relationships, but there's also those relationships between heat and all of these other kinds of things, and event and ritual. So, for example, the campfire, cooking, different kinds of social elements are around this whole notion of when we, as humans, discovered fire, that changed the way that we ate, it changed the way that we socialized, and the fire, beyond just the heat, in that kind of sense, started to become also a social practice. Something like the barbecue or something like cooking together. So I think that there may be some aspects of that from a ritual perspective that you guys may want to consider. And I'm suggesting that because I think when we start to think about how we use the kind of elemental, I think we can be open at this stage to different aspects of how humans have utilized this in different ways, right? So with the water team, which is almost the opposite of you guys, water has also a function of bringing people together, right? So when we were looking at the step wells, all of that stuff. And I would say fire has the same, but for different purposes. It's not for thirst and it's not for bathing. It is for cooking and it is for heat. So those differences manifest themselves in different kinds of architectures. And I would try to think a little bit about how those things have been used from very conventional buildings, like you guys talked about the chimney and these kind of things. And you mentioned that, this happens in the West and it happens in China. It would be very useful for me to know how it happens differently. And some architects have always been very sensitive to this. So for example, someone like Frank Lloyd Wright, when he was designing his houses, all of his architecture was around the fireplace, because for him, the fireplace was the heart of his buildings. And it's interesting that it had certain values, organizationally speaking, for an architect like Frank Lloyd Wright. But it had a very particular value when one was talking about the home or the house. His architecture revolved around fire, for example, organizationally. So I think when you guys are thinking about this, both the literal fire and when you're looking at the aspects of light and heat, I think it's really useful to look at them in the history of architecture, in the history of the kind of social structures that are around this. And I would also say in the history of the technologies. So for example, you mentioned some of the things, but I would frame them in a way where we can start to look at very, very different models. What I like about the presentation is that we can go from fireworks to thermal scans to the fireplace, all of these different elements. If we didn't have that connection, would not be able to kind of offer us all of these different ways of thinking about it, right? And I think the byproduct of light and heat, are your mediums as well. So I think some of the architecture that you guys used, I think is really talking about those thermal things, sometimes more literally than others. And so I would look at the contemporary examples that you showed, but I would also try to expand that a little bit more. Maybe some of the things that we take for granted under those kind of circumstances mean something different. And the Shumi example, the reason that I show it is that even like the first team when we were talking about space, you can't really model the firework, right? It's one of those things which is really about chemical reactions, and it's also about, notation systems of sequencing and choreography. So it's more like a dance notation than it is about explicit control in some ways, right? Because in some ways you're designing a notation system, a sequencing, and a certain almost like a cooking strategy, right, of ingredients to play with color, to play with explosion, And I think all of those things which are really instantaneous, I think is also super interesting. So I would ask you to maybe take some of these examples and try to organize them. Some which are more event-based and immediate, some which are maybe more architectural and are organizing space. And to think about the organization of space in terms of the social interaction of space. So the difference between a fire in nature and internalizing that in the fireplace, and try to look for opportunities that we can speak to this. And the material properties of what we're burning, I think also has a residue in terms of the ash and in terms of the use of how we can use them as materials as well. So I think in your scope, I think that there is something about controlling the environment, like heating air is very different than heating water, right? In some ways, in terms of the tools. You guys were showing things like the radiator and other stuff like this. I think all of those things are important, but I would ask you in particular to look at this Rainer Banham book called Architecture and the Well-Tempered Environment. You can find it online. If I find the link, I'll send it to you, but you should be able to find a PDF of this. And the reason that I'm saying that is because Rainer Banham tried to write a book about controlling the environment. Primarily what he meant was about conditioning the environment, primarily through heat, because he felt that heat equated to comfort. And, you know, he also utilized air and talking about that as well, but from a perspective of air conditioning. So even the differences between the air team and yourselves, I think just look at about the strategy that there is no fire without air, right? Like oxygen, I should say. And I think like in that sense, try to see what the meaningful relationship between those elemental aspects are. So I know that this isn't like so specific about, okay, let's make fire structures or things like this. You don't have those direct references, but you do have, I think, a lot of social organizational references that are very, very close to a lot of types of architecture. And I think if you look at something as simple as the fireplace and how that has been dealt with in an individual level or in a distributed way based on the architecture, and you look at stuff like what Bernard Schumi was talking about relative to the fireworks, I think we will start to organize a way to think about how our architecture is really dealing with the instantaneous, the chemical transformations that have both the material properties, but also this kind of almost explosive reactionary way of thinking about computing. So in some ways, I would almost think that a strategy to think about how fire could work is more like a strategy that we would look at chemical computing as a way of thinking about things. So in this case in particular, stuff like reaction diffusion and these kind of strategies that have instigation point and dissipation points, I think are really important. So you know when something heats, it dissipates, right? So it can get cooler. So you see that over a period of time, things cool. It's because the warm air has expanded. It's moved away from the source of the material to allow for that cooling. So I think those kind of things are the kinds of things that we're going to have to start to try to simulate. And in some ways, I think the air team and yourselves have, I think, strategies that are very similar in terms of computation, because they are really talking about things that are not really contained. They're more atmospheres, right? Does that make sense to you?
Yeah.
I mean, like the Sky Ladder, I mean, also for the rest of the teams, I think it's useful. They did a nice documentary on Netflix on Sky Ladder. And maybe the thing that's most important about his work, and I apologize that I cannot pronounce his name very well. I always make it sound like something totally different. So maybe you can explain to me how to say his name.
You mean the
artist?
highlighter?
Yeah, the artist.
蔡国强.
Yeah, that's why I can't say it. Taiko-chan. I'm gonna practice. You guys are going to have to teach me some Chinese. But what I really like about the documentary is how he includes people around this, right? Everybody knows what fireworks are, but he is really using it as a way to bring people together, as a kind of, the power of creating space through event is that it brings people together for a moment in time. Do you understand what I mean by this?
Yeah.
What I like about the documentary is like you see the story of all the people working together, and you see the story also culturally speaking about what fireworks have meant, which also means something very different in the West. Of course, there is a celebration, and of course some people relate to it as a war and gunpowder and all of these kind of things. So it has a very powerful social relationship. What I like about it is that spatialized. That's what Shumi liked about it, that the event of designing the fireworks created the opportunity to really truly speak about an event architecture. So he didn't think that these red follies at the end of the day was really what the event of that architecture was. And I think in some ways, it's interesting to see where you guys will put some emphasis. The Philip Rom way has a particular trajectory. The Bernard Shumi way has a particular trajectory, but I think that there is something maybe more fundamental in what you're talking about. With ash, with nutrients, with growing, and that's why I'm showing you stuff like Dan Rosengard and some other things that you guys can have a look at. I mean, he's an interesting artist anyway, which I would suggest that the studio looks at. I'm trying to invite him to one of the events that I'm doing, but you can start to see some of the things that he's working on. A lot of his work, I think, very much is dealing with energy. So I would suggest that you guys have a look at some of this stuff. You know, he tries to make sidewalks that basically create light or self-illuminating, these kind of things. Some of the stuff is interesting. Some of the stuff is not so interesting, but, you know, overall, I think he tries to understand the subject pretty well. So whatever he's working on generally has some intelligence to it. So I would have a look at his things. I would have a look at Bernard Shumi. And yeah, we'll see where the next presentation goes with some of the research. But I would try to kind of organize also the aspect of cooking, the idea of coming together for food as a strategy as well. Does that make sense to you, or does that sound too strange for you?
Yeah, I think it's really clearly.
Okay. I'm just asking because sometimes I don't want to just provoke you in saying something if you don't understand. So I just think, like, architecturally speaking, the whole idea of food culture is really something that was born out of using this elemental aspect of fire and heat. And it connects to nature and to things that are very culturally connected. So I feel like there's an opportunity to look at that part as well. I'm not sure how we use it yet, but I think socially organizing it around this, I think, is very, very powerful. Because in some ways it's also an exchange. It's also very cultural. And also the ways that we think about that stuff, I think, would have a different way of how we could actually think about what would make something more prototypical. Food is also so connected to social that is usually the easiest way to have conversation or to meet people from different culture. It's usually our introduction to things as much as is architecture, right? So people take you to buildings, maybe performances, but for sure it's about the food and the ritual around those things. And somehow I think that there is something interesting to keep in the back of the mind about this process. Okay. I know it's pretty late for you guys, and I'm sorry. I will try to make the meetings a little bit earlier, but this week my mornings have been so full of meetings. But is there any other questions? And just to say that other documentary that I was mentioning is for Biosphere 2. It's called Spaceship Earth. As I look at Biosphere 2. Jesus. I'm not going to play this because it's super loud. But anyway, it's really about trying to develop a strategy which was looking at a lot of these kind of technologies and what it means socially to live together in those kind of closed environments. So this was really like 60s, 70s experiments about creating an ecosystem and an ecology. And so you see these people locked in this kind of space, and you see some of the social aspects of a lot of those things and how that stuff plays itself out. So it may be something interesting for all of you guys to watch as well. Some things are interesting, some things are also the difficulties of the human condition, how people behave, how people respond to each other. So that's where this kind of aspect of trying to have a much more engaged relationship with nature and things, I think, is important. Okay? Does that make sense?
Yeah.
Is there any other questions for you guys from any of the teams? I'll stop sharing this. I thought it was a good presentation. I think all of the teams have a lot of interesting stuff. I think the thing that's very important is to try to structure things so that they somehow have like the next step of the research, or how can we, organize things so we can go deeper into some subjects, and maybe some other things that were helpful but maybe are not so useful anymore, we can put them aside. So I think like between the different teams, I think there were strategies of organizing things. Sometimes it was material, sometimes it was environment, sometimes it was the model of computation that potentially we could be looking at. I think if we can start to organize those structures a little bit, I'll share this video after it is so that you guys can just look at each of each other's structures, and whatever is the clearest way to kind of organize, I think we can try to organize the groups under those headings, if that makes sense. I'll ask Apo to send you a sample InDesign file. That's just for template size. You don't have to use the same fonts and all of those things, but I think it's useful that it has the same format in some way. That way we could really organize all of this material in one way and present it like a whole Earth catalog. So the diagramming techniques, the things that you guys can do to synthesize the material as some of these ideas are becoming clearer, I think it's important. So the same way that you do a catalog for a workshop, if you surveyed all the different ways of thinking about, air structures, for example, like if I have one spread and I see all the different air structures, like air beam structures, for example, versus other things, you could start to catalog very quickly the history of existing architecture with this elemental aspect. Some may be very old school vernacular, some may be very contemporary. You can start to really map all of these things together, and I think that this will be positive. So I like the diagramming parts. I like a lot of the references. I think a lot of them are super interesting, so we should go a bit deeper into those things and push the work with Unity. I think Houdini is a good tool, particularly for the fire team and the air team. But it could be for other teams as well, to be honest, because it's really particle based. But let's see where it goes. I mean, each of you guys have had some strategies for this stuff. It's not so important to have multiple platforms for a lot of things. So, I mean, Alex is comfortable in Maya. Octavian is a Unity guy. Mustafa is definitely a Maya guy. But I think some of these other tools we can also introduce, but just do it as a studio. It doesn't have to be taught to you, okay? But I think we can help each other to learn how to use Houdini, for example, or learn how to use Touch Designer, which Apo is going to start to look into. I think with Touch Designer and those things, maybe we sort of not put it to the side, but we try to explore it in a different way, not so much about physical or tangible prototyping, but more about information and extraction and data. So we'll keep an open mind to those things. That's all. Okay. Okay, so since it's nighttime for pretty much everybody now, and we'll call it early morning for some, I'm not going to keep you any longer. I'll send an email out to you guys. We should try to meet next week, probably around the same time, to kind of review this next stage of work. And do you guys have a meeting with Mustafa this week? When is that, may I ask?
We haven't received any email, but he had said that it's going to be a regular meeting or something like that.
Yeah, Mustafa and Apo, they'll be meeting regularly with you. Octavian, I think, has been doing his sessions, no? In the morning. And yeah, Alex will start working with you guys too, both in Unity and in Maya. So there's going to be a lot of parallel processing things, but that's how the studio works, basically. In the beginning, everything all over the place. Slowly, we get to move through that material, and by the end of the term, the goal is that we have a clarity of what we're working on in some way. Okay. Is there anything that you guys want to ask me? Anything outside of what we talked about?
Yeah, a small question. Do we have a MeetWithTheo presentation next week?
Well, I mean, I think realistically speaking, we should. I mean, technically, we do. I'm going to double check with the tutors just to see where they are in terms of how they're working with their students. I mean, from my side, I don't think it's a problem for us to have a presentation. The question is how we structure the presentation to really talk about the kinds of issues that you guys are working on. But I want to see that it's something meaningful. If it's not next week, it'll be in a couple of weeks. So whenever it seems to be a better opportunity to actually review work. I know some of the tutors are trying to do something specific, and I'm not sure a critique is going to be helpful. Would it be helpful for you guys? Would you guys want the presentation next week, or would you want it in a couple of weeks, or what's the thought from your side?
I think that we are in, we have too many things open and we don't have a very specific direction. In that sense, I'm not sure how helpful. I mean, always to present is helpful because you have to organize some things, but in order to be well structured and clear. But in terms of feedback, I don't know. I'm not sure.
I mean, I have to be honest with you, like this term, I'm not sure if a midterm in a generic sense is very useful. I mean, I'm sure it's more useful for, let's say, Patrick's studio, because in some ways they're continuing what they've been doing in a very literal sense. In our sense, honestly, we're trying to figure out what we're doing. Meaning, on the one hand, obviously, it's pretty clear and super interesting, and maybe there are some examples that people can give you to look at. But I have the confidence that you guys are doing that already between yourselves. And I also think between the conversations you're having with me and the others, I think we're just starting to figure out what are tools, what are the kind of concepts that we're developing. So I don't have a real urgency for that. I would leave it more flexible from my side. I'll double check with the other two just to see if it's something that's useful. I'm pretty sure they're going to say exactly the same thing that you guys are saying to me now, that, you know, nothing is really clear to critique yet. So even if they're doing some basic, you know, grasshopper work or this or some Maya work, then that's not something that's too useful to critique at this stage. So they're doing studies from what I know. So leave it to me. Regardless, let's say you're going to have a presentation to me, let's treat it more informally, or we can treat it very formal, try to structure it as much as possible from this conversation, let's say. And yeah, we will continue the discussion, basically. If we do have the jury next week, I'll let you know immediately. I mean, I'll speak with Sajay and Patrick. I don't think it's going to change the way that you guys are producing stuff. I would say that it will change a lot how long you present, because it's pretty for sure that we're not going to have an hour presentation per team. That would be about 15 and 20 minutes. So even to get to that in terms of streamlining things and editing your work and getting it to a place, it's not a bad thing to do. So we should focus on trying to do that anyway. By you guys taking some decisions of what's important and what's not. And yeah, if we share that with the other guys or not, I'll let you know. Okay, does that make sense? So don't stress over the presentation, but on the other hand, edit things and try to take some decisions so that this gets into a place where it's more clear what are the main things driving the project, right? Okay, guys. Anyway, it's good to see you all, and yeah, we're going to keep it going. Good luck, good conversation, good presentations. It's good to see that you guys are taking decisions and exploring stuff. I think it's making the presentations also much nicer when you guys come to the table with a lot of things. So keep doing that, but try to get deeper into things. I want us to become experts in what we're talking about. And that's why you guys need to use diagramming techniques and other techniques to kind of make that information more legible and quicker to go through. So don't lose the richness of the material, but just try to have a synthesis of it. And some of the things like we talked about that kind of reinforce some of the big picture problems that are so obvious, I think we can accept that that's pretty common knowledge. Okay? All right. Okay, guys, then I wish you a good night, get some rest, and there's always tomorrow. See you.
And thank you.
Good night. Good night.
Good night.